Soy Leonardo López Luján, miembro del Colegio Nacional, y quisiera invitarlos a todos ustedes a asistir al ciclo de conferencias La Arqueología Hoy. Para este año de 2020 hemos preparado un riquísimo programa en el cual invitaremos a los protagonistas de la arqueología para que nos hablen de sus descubrimientos, no solo en México, sino en otras áreas como Guatemala, Perú y España. Hemos elaborado un programa muy interesante que irá desde las cabezas monumentales olmecas hasta los vasos funerarios hallados en las pirámides de las selvas mayas. También abordaremos la última tecnología que se aplica en la ciencia arqueológica. Entre otras técnicas, se platicará acerca del LiDAR, de los drones y cómo estas técnicas contribuyen a un mejor conocimiento de las civilizaciones antiguas. Las conferencias tendrán lugar en el aula mayor del Colegio Nacional, aquí en la calle Donceles, en el Centro Histórico de la Ciudad de México, y la entrada es libre. Los esperamos a todos. Muchas gracias.
Cualquier pretexto es bueno para visitar el centro histórico de la Ciudad de México. Hay edificios maravillosos, rincones que usted jamás ha visto y desde luego hay sitios que son de visita obligada. Me refiero al Colegio Nacional. Un espacio donde se junta la inteligencia, la imaginación, el arte, la ciencia y algo muy bonito, la conversación y la amistad. En este edificio hay ahora un nuevo espacio. Es luminoso, es grato, es agradable y está el mejor amigo de usted, mío y de todos nosotros. ¿Sabe qué es? Un libro, muchos libros, una historia, muchas vidas que van a enriquecer la nuestra. Vengan a visitar la librería del Colegio Nacional.
Sí, me parece lindo.
armies have been destroyed by Spartacus.
Spartacus, a motion picture unequaled in the entire history of filmmaking, unlikely ever to be surpassed. In the tenderness.
Have been destroyed by Spartacus.
Spartacus, a motion picture unequaled in the entire history of filmmaking, unlikely ever to be surpassed. In the tenderness.
Soy Leonardo López Luján, miembro del Colegio Nacional, y quisiera invitarlos a todos ustedes a asistir al ciclo de conferencias La Arqueología Hoy. Para este año de 2020 hemos preparado un riquísimo programa en el cual invitaremos a los protagonistas de la arqueología para que nos hablen de sus descubrimientos, no solo en México, sino en otras áreas como Guatemala, Perú y España. hemos elaborado un programa muy interesante que irá desde las cabezas monumentales olmecas hasta los vasos funerarios hallados en las pirámides de las selvas mayas. También abordaremos la última tecnología que se aplica en la ciencia arqueológica. Entre otras técnicas, se platicará acerca del LiDAR, de los drones y cómo estas técnicas contribuyen a un mejor conocimiento de las civilizaciones antiguas. Las conferencias tendrán lugar en el aula mayor del Colegio Nacional, aquí en la calle Donceles, en el Centro Histórico de la Ciudad de México, y la entrada es libre. Los esperamos a todos. Muchas gracias.
Cualquier pretexto es bueno para visitar el centro histórico de la Ciudad de México. Hay edificios maravillosos, rincones que usted jamás ha visto y desde luego hay sitios que son de visita obligada. Me refiero al Colegio Nacional. Un espacio donde se junta la inteligencia, la imaginación, el arte, la ciencia y algo muy bonito, la conversación y la amistad. En este edificio hay ahora un nuevo espacio. Es luminoso, es grato, es agradable y está el mejor amigo de usted, mío y de todos nosotros. ¿Sabe qué es? Un libro, muchos libros, una historia, muchas vidas que van a enriquecer la nuestra. Vengan a visitar la librería del Colegio Nacional.
¿Te gusta esto, Juan Pablo? Sí, me parece lindo.
destroyed by Spartacus.
Spartacus, a motion picture unequaled in the entire history of filmmaking, unlikely ever to be surpassed. In the tenderness.
Have been destroyed by Spartacus.
Spartacus, a motion picture unequaled in the entire history of filmmaking, unlikely ever to be surpassed. In the tenderness.
Soy Leonardo López Luján, miembro del Colegio Nacional, y quisiera invitarlos a todos ustedes a asistir al ciclo de conferencias La Arqueología Hoy. Para este año de 2020 hemos preparado un riquísimo programa en el cual invitaremos a los protagonistas de la arqueología para que nos hablen de sus descubrimientos, no solo en México, sino en otras áreas como Guatemala, Perú y España. hemos elaborado un programa muy interesante que irá desde las cabezas monumentales olmecas hasta los vasos funerarios hallados en las pirámides de las selvas mayas. También abordaremos la última tecnología que se aplica en la ciencia arqueológica. Entre otras técnicas, se platicará acerca del LiDAR, de los drones y cómo estas técnicas contribuyen a un mejor conocimiento de las civilizaciones antiguas. Las conferencias tendrán lugar en el aula mayor del Colegio Nacional, aquí en la calle Donceles, en el Centro Histórico de la Ciudad de México, y la entrada es libre. Los esperamos a todos. Muchas gracias.
Cualquier pretexto es bueno para visitar el centro histórico de la Ciudad de México. Hay edificios maravillosos, rincones que usted jamás ha visto y desde luego hay sitios que son de visita obligada. Me refiero al Colegio Nacional. Un espacio donde se junta la inteligencia, la imaginación, el arte, la ciencia y algo muy bonito, la conversación y la amistad. En este edificio hay ahora un nuevo espacio. Es luminoso, es grato, es agradable y está el mejor amigo de usted, mío y de todos nosotros. ¿Sabe qué es? Un libro, muchos libros, una historia, muchas vidas que van a enriquecer la nuestra. Vengan a visitar la librería del Colegio Nacional.
Sí, me parece lindo.
Been destroyed by Spartacus.
Spartacus, a motion picture unequaled in the entire history of filmmaking, unlikely ever to be surpassed. In the tenderness.
destroyed by Spartacus.
Spartacus, a motion picture unequaled in the entire history of filmmaking, unlikely ever to be surpassed. In the tenderness.
Soy Leonardo López Luján, miembro del Colegio Nacional, y quisiera invitarlos a todos ustedes a asistir al ciclo de conferencias La Arqueología Hoy. Para este año de 2020 hemos preparado un riquísimo programa en el cual invitaremos a los protagonistas de la arqueología para que nos hablen de sus descubrimientos, no solo en México, sino en otras áreas como Guatemala, Perú y España. Hemos elaborado un programa muy interesante que irá desde las cabezas monumentales olmecas hasta los vasos funerarios hallados en las pirámides de las selvas mayas. También abordaremos la última tecnología que se aplica en la ciencia arqueológica. Entre otras técnicas, se platicará acerca del LiDAR, de los drones y cómo estas técnicas contribuyen a un mejor conocimiento de las civilizaciones antiguas. Las conferencias tendrán lugar en el aula mayor del Colegio Nacional, aquí en la calle Donceles, en el Centro Histórico de la Ciudad de México, y la entrada es libre. Los esperamos a todos. Muchas gracias.
Cualquier pretexto es bueno para visitar el centro histórico de la Ciudad de México. Hay edificios maravillosos, rincones que usted jamás ha visto. Y desde luego hay sitios que son de visita obligada. Me refiero al Colegio Nacional. Un espacio donde se junta la inteligencia, la imaginación, el arte, la ciencia y algo muy bonito, la conversación y la amistad. En este edificio hay ahora un nuevo espacio. Es luminoso, es grato, es agradable y está el mejor amigo de usted, mío y de todos nosotros. ¿Sabe qué es? Un libro, muchos libros, una historia, muchas vidas que van a enriquecer la nuestra. Vengan a visitar la librería del Colegio Nacional.
Sí, me parece lindo.
Have been destroyed by Spartacus.
Spartacus, a motion picture unequaled in the entire history of filmmaking, unlikely ever to be surpassed. In the tenderness.
Have been destroyed by Spartacus.
Spartacus, a motion picture unequaled in the entire...
Buenos días, mi nombre es Luis Felipe Rodríguez, soy miembro del Colegio Nacional y me es muy grato darles la bienvenida a todos. Déjenme, me paso al inglés en deferencia a nuestros invitados. My name is Luis Rodríguez. I am a member of the Colegio Nacional, and I'm very pleased to see you all here for this event. Let me just say a few words of El Colegio Nacional. It was founded in 1943 by the then President of the Republic, Manuel Ávila Camacho. And at present, it has 40 members, of which roughly 10 are from the physical sciences. That's my case, I'm an astronomer. 10 are from the biological sciences, 10 are from the social sciences, and the last 10 members come from the arts and literature. So our mission is to make meetings like this, although I would say that we usually prefer doing meetings for the general public, but occasionally we do meetings for a very highly specialized level, as it is this case. So thank you very much for being here, and try to check our page. We are all the time doing meetings on various things, on arts, on sciences, and it's interesting that you become involved, and whenever possible, come and visit us here, or see us by video conference, as it is the case of this meeting that is being transmitted simultaneously, and it is possible for a person anywhere in the world to connect and see the meeting. So let me give the word to my friend and colleague, Lorenzo Díaz Cruz, who will tell us a little more about the logistics of the meeting. Lorenzo.
Okay, thank you. Welcome, everybody. We will have a busy day today. I want to say in the first place that this event was made possible by the effort of an organization and negotiations of Luis Felipe. So I'm very grateful for his support, and because as he said, he's a radio astronomer, but he has a broad view of science and what needs to be done. I think really that's the kind of leadership that we need in Mexico in these years. So the program will include, as I said here, plenary talks by Lance Dixon and Zvi Bern, who were recipients of the Sakurai Prize in 2014, if I'm correct, with David Kosover for their work on scattering amplitudes. And I always wanted to have some activity along these lines. I myself want to move and to do a bit into that. So I think this is a great opportunity for especially for the young people, young in spirit and in age. So we'll have a very interesting day. The conference includes a broad range of research topics in quantum field theory and some of applications. So for the very, very young people, I will say quantum field theory is almost 100 years old. It combines quantum mechanics and special relativity, and it was started by the same founding fathers of quantum mechanics, Heisenberg, Pauli, Jordan, Dirac, et al. Later on, the first complete quantum field theory was quantum electrodynamics after the work of Feynman, Schwinger, Tomonaga, Dyson. At the very beginning of quantum field theory, it was looked with a bit of hesitation because of the problem of infinities, and it was precisely the contribution of Feynman and company that proved that the QED is a renormalizable theory. And thanks to that, quantum field theory is accepted as the framework to study many phenomena in nature, ranging from particles to astrophysics to even condensed matter, and there is a relationship between all these areas of application. So now our best quantum field theory is the standard model, which describes the quarks and leptons as the fundamental constituents of matter and their interactions, electroweak and strong. The standard model, as most of we know, was confirmed with the discovery of the Higgs boson at the LHC in 2012. The standard model phenomena, to describe it at LHC, including the Higgs phenomenology, requires very complicated calculations of perturbative QCD and the like. And precisely in this topic, new techniques in quantum field theory have been developed since the 80s and 90s that were very useful to study the phenomena at the LHC. But the full power of these methods was understood more recently and viewed precisely by the work of our speakers. So these days in this area we have new terms like maximal helicity violation, unitarity code, scalarity relation, BSW, double copy, amplitude hadron. So those are the new terms that we hear in the modern quantum field theory, and maybe we will hear today. So this subject has many groups in the world that are doing very active in this topic of scattering amplitudes in the United States and Europe. In our country, in Mexico, quantum field theory arrived somehow late. The first studies of QED were done in the 60s. And the first one-loop calculation within the complete standard model was done in the mid-80s, so kind of late compared with what was done in the US or Europe. But currently we have some groups in Mexico that are doing research in the area. They touch different aspects of quantum field theory, applications, and even string theory. And some of the speakers in our sessions today are precisely from those groups in Mexico that are somehow representative of several parts of the country. And I also want to thank all of them for coming, making the effort to spend time here and discuss and contribute to the meeting. But the main goal of the meeting, as I said here, is to learn from the experts and to motivate the young generations. In the young generations, we can include even the Andres Luna postdoc at UCLA, who will tell us about the square root of a black hole. And also Brian Larios, who is in Honduras, but I consider him part of the Mexican community. He's a representative in Honduras. And now James Edwards also will talk on the new acquisitions in Mexico. A kind of measure of the interest in the field is that we have, until today, we have around 72 participants in the meeting. So I think it's a promising number and a promising hint of the future of the area in Mexico. So before starting with the talk of Lance, just let me say something that he wrote in this as a guest contributor to the blog of Sean Carroll. And he says, in short, our work was about computing things that could in principle be computed with Feynman diagrams, but it was much more efficient to use some general principles instead of Feynman diagrams. In one sense, the collection of ideas may be considered just tricks because the general principles have been around for a long time. On the other hand, they have provided results that have in turn led to new insights about the structure of gauge theory and gravity. They have also produced results for physics processes at the Large Hadron Collider that have been unachievable by other means. And he used this quote that he says that it has inspired him for his career, that I also like very much, by Landau, that says, a method is more important than a discovery, since the right method will lead to new and even more important discoveries. So I hope that I was not a spoiler with this, taking his own words to begin this meeting. Okay, so we'll start.
Gracias. Yo estudio español en la escuela, pero más de 40 años. So I hope you don't mind if I switch to English now. It's a great pleasure to be invited here. When I was younger, I had two chances to maybe come to Mexico City, one to play badminton and one to climb mountains, but I didn't end up doing either of them. So it's great to finally have a chance to come here. And thanks a lot for that nice introduction, Lorenzo, but it's actually a little embarrassing for the following reason. That quote you listed by Landau, I do love that quote. And I was asked by Roger Blanford and Kip Thorne. Kip Thorne got the Nobel Prize for his work in gravitational waves. Anyway, they were writing a book on classical physics, which had a lot of methods in it, and they wanted to use this quote at the beginning of one of the chapters. So they asked me, where did you find it? Where was it from, where did Landau say it? And I found it on one of these quote aggregator websites. So then I did a little research, and I talked to Misha Schiffman, who edited a book about Landau, and he talked to a historian friend of his, and the bottom line was there's no evidence that Landau ever said that. So, but anyway, it is a great quote. So I wanted to talk to you today about one application of the field of scattering amplitudes, which is sort of the one that motivated Zvi and David and me to get interested in this subject quite a while ago. And that is their application to the study of physics at the energy frontier, where the highest energy collisions made by man are taking place. And those are generally these days at hadron colliders. And the principal hadron collider right now is the Large Hadron Collider, which collides protons together. And it's exploring this energy frontier. And in order to make the best use of this collider, a lot of theory is needed, basically to understand what the standard model, which was mentioned by Lorenzo, predicts in order to try to uncover new physics that goes beyond the standard model. So I want to tell you some of that story today. So here's a picture of the ring, or where the ring is, that represents the Large Hadron Collider. It's 27 kilometers in circumference. It inhabits 2 countries. That yellow jagged line there is the border between France and Switzerland, and France is on the left, roughly, and Geneva and the Geneva airport you can see on the right. And the protons circulate around this ring after building up their energy in smaller rings that you can also see there. And there are a number of collision points where they undergo very violent collisions, and you can see at least 4 detectors listed there. And the ones that are more interesting for my talk are ATLAS and CMS. And they are really exploring the highest energy collisions that you can make in a controlled situation in the laboratory. And this machine represents an increase in capacity over previous machines in 2 ways. One is in the energy. Its center of mass energy is 13 going on 14 in a few years tera electron volts. For comparison, the mass of the proton is about 1 giga electron volt, or GeV. And so the rest energy in this collision is about 14,000 proton masses. And so you can make a lot of particles in such collisions, and you might be able to make very heavy new particles. Another way in which this is an advance over the Tevatron, which was a machine at Fermilab in Illinois, is in the collision rate, or the luminosity. This machine produces 100 times as many collisions per second as the Tevatron was capable of doing. And so those 2 things give it a new window that lets us explore physics at the shortest distance scales. And it's been operating since 2010, or about a decade. And in the past 8 years or so, it's been working very well. It's exceeded the design performance in terms of the number of collisions per second. And what you see here is something called the integrated luminosity, but that's directly proportional to the number of proton collisions that it's accumulated and been able to study. And the more collisions you have, the better your data, the better your statistics, the more precisely you can measure things, the more you can look for the unknown. As you can see in the early years, it took a little while to get up to this high collision rate. But in the last 2 years, 2017 and 2018, it was producing a lot of data. The unit used here by particle physicists is called inverse femtobarns. It's a pretty funny unit, but way to remember it is that if you have 60 inverse femtobarns, you could see one event. If a cross-section is a probability for a collision taking place, and it has units of area. And a barn is only 10 to the minus 24 square centimeters, so that's pretty small. But a femtobarn is 10 to the minus 15 of that. So we're talking about 10 to the minus 40 times this size. That's the kind of probabilities of things happening that we can look at with this machine. So Lorenzo mentioned the standard model, and that's our basic framework for understanding everything that happens at the Large Hadron Collider and in most of particle physics. And what the standard model does, in very brief, is it puts all of the elementary forces that we know about, except for gravity, into the same basic framework. And the particles of the standard model, excluding the Higgs boson, can be laid out in a kind of pattern like this, where these guys here are the particles of matter. The up and down quarks live inside the proton. The electron, you know, from its role of carrying electrical currents and so on. And then there are heavier cousins of the same particles that have very similar properties except for their masses, which usually cause them to decay very quickly. So these are in the province of accelerators. We only really see them there pretty much. Then there are the force carriers, and that includes the photon for electromagnetism and the weak bosons, which are W's and Z's for the weak force. And then the gluon. The gluon is the carrier of the strong force. The guys up here, the up and down quark and their cousins, the heavier quarks, they all feel the strong force. And that strong force binds them in ordinary matter into nucleons, into protons and neutrons, and also a little bit heavier particles or other particles called mesons that decay. And we have a basic picture for all of these forces in which we describe them using Feynman diagrams, which we'll come back to later, but their essence can be described by a single Feynman diagram, which describes which particles they talk to. For example, electromagnetism talks to electrons, not surprisingly. So there's a vertex in a Feynman diagram that describes this coupling. But it also talks to quarks because quarks, like electrons, are electrically charged. The weak bosons talk to many different particles, in fact, basically to all of the matter particles, and they cause things like radioactive decay. So a decay of a proton to a neutron plus a positron and a neutrino could be described in this way, moving upward in time. And then the strong force describes the interaction between quarks in QCD. And because the strong force is strong, it's the main player in LHC collisions. We often are interested in looking at things that are related to the weak force, but the strong force produces huge backgrounds that we need to understand very well. And as was mentioned by Lorenzo, the crowning achievement of the Large Hadron Collider to date has been to discover the last missing particle of the standard model, the Higgs boson, which was proposed in 1964, and it took almost 50 years to discover it. The discovery was announced in 2012. Here is some of the evidence that led to the discovery. What is shown here is plots from the two detectors participating in the discovery, ATLAS and CMS, and it shows the invariant mass of two photons. So you detect two photons coming out of the collision, and you add up their energy and momentum, which relativistically are a 4-vector, and you can combine them and construct an invariant called the gamma-gamma invariant mass. And if it's a Higgs boson, it should peak at a particular place, and you can see that it does. It peaks at about 125 GeV, or 150 times the mass of the proton, roughly. And so that is evidence of this new particle. You'll notice that it's not background free. There are a lot of particles, a lot of photon pairs that have nothing to do with the Higgs boson. But and they're produced by what we call sort of QCD processes, quark anti-quark annihilation. Anyway, they produce a smooth falling background, and you can identify this bump on top of the background. That is actually one of the cleanest ways to see the Higgs boson. There is one other clean way, but the Higgs has been seen in many other ways, many of which are much dirtier or harder to extract. So this is one of the cleanest signals for the Higgs. Now, as I mentioned, the Higgs was predicted in 1964, and two of the theorists were around to celebrate, Francois Englert and Peter Higgs, and they received the Nobel Prize soon after this discovery, which the experimentalists were glad to provide them with. So that completes all the particles of the Standard Model. But we know the Standard Model isn't the final answer. There are a lot of questions that it doesn't answer properly. And one of the questions it doesn't answer, it doesn't have a candidate for dark matter. We don't know for sure that dark matter is an elementary particle. It might be something much more complicated. It might be made out of elementary particles in some other sector, or it might be a single kind of elementary particle. But if there is an elementary particle, and if it has something to do with the weak scale, the scale at which the W's and Z's get their mass, the LHC might be able to produce it, or produce some other particles that decay to it. This is some evidence for dark matter in the galactic rotation curves. As you move out and you calculate the forces from the visible matter here, you expect the velocities of galaxies to be on this curve, but instead they're much higher. And there's pretty compelling evidence for dark matter, not only in the halos of galaxies, but also between clusters of galaxies. This is a collision between two clusters called the bullet cluster, which shows that the collision has moved the ordinary matter in red and separated it from the location of the dark matter as inferred by gravitational lensing. So there's pretty compelling evidence that dark matter is out there, and it would be great if we could produce it in the laboratory. So the LHC has been searching for dark matter. Now, it's also been searching more generally in the context of physics beyond the Standard Model. There's a theoretical problem with the Standard Model, which is called the hierarchy problem. In the Standard Model, the electroweak scale, the masses of the W's and Z's look very fine-tuned if you could imagine going to energies much above them, to thousands of TeV. And in other words, if you try to calculate and you put a high energy cutoff of 1,000 TeV, typically the Higgs potential that you get causes the Higgs and W masses all to rise up near the cutoff. And so it's a puzzle. And many theories have been developed to try to solve this puzzle, and they all have to, essentially, almost all, have a host of new massive particles with masses that are within reach of the LHC. So that was one of the compelling arguments, besides the Higgs boson, to build such a collider. Now, you can suppose this red particle is a new particle, and suppose you could produce it singly. This is actually difficult because then these effects typically disrupt precise measurements in an electroweak sector. And so it's much more likely that these new particles should be pair-produced. Then their precision electroweak effects are much smaller. And so such theories often have a discrete symmetry that tells you you can't make the new particles one at a time, you have to make them two at a time. In that case, if there is such a symmetry, then the lightest particle that it carries a non-trivial odd quantum number under that symmetry becomes stable and could be a dark matter candidate. So there are a lot of theories out there that contain within them dark matter candidates. One of the types of theories is called supersymmetry, but there are other flavors of new physics at the LHC that could be seen at the LHC. And if you want your theory to make a big dent at the LHC, you usually have some cuddle, plus potentially dark matter. More generally, you never see the new physics particles directly. They're either very stable or very unstable, and so you typically just see their decay products. And so then you need to distinguish their decay products from the production in the standard model. Now, one example that has been studied and searched for a lot at the Large Hadron Collider is a theory called supersymmetry. In this theory, there's a symmetry between matter, made out of fermions, and forces, which are carried by vector bosons. So it relates spin 1 to spin 1/2, and also to spin 0. So every integer spin particle, or boson, has a spin 1/2 partner. And so there have been many searches for the particles of supersymmetry at the Large Hadron Collider, and indeed at many other machines. But these searches are not free of backgrounds. There are always standard model cross-sections that look very much like the new physics cross-sections. One example, this is sort of a classic signature of dark matter within supersymmetry. You can have two protons come in, and because these particles, gluinos, they are the partners of the gluons, and they have a very big color charge. So if they're light enough, they will be produced very copiously. There will be lots of gluinos. But the gluinos will decay. They actually have to get rid of their color charge because the lightest supersymmetric particle, which would be a WIMP or an LSP, it has no color. It only has weak interactions. So the gluinos have to get rid of their color, and they can do it by radiating two quark jets. And so you get what's called a SUSY cascade, and you get two quark jets. But then you also get these very light particles, these lighter particles, lighter supersymmetric particles, but they escape the detector. So you don't see them directly. Instead, if you look at the detector from the point of view of the beam going into the screen, you see four jets come out, and they're imbalanced. So the momentum was conserved, but some of it was carried off by invisible particles. So this is called, for some reason, missing transverse energy, or MET, plus four jets. So that's a very canonical, very standard way to search for supersymmetry at the LHC. And it would be great if that was the only thing that could produce such an event, but it's not. Quite often, you make a Z boson at the LHC. We'll see in a second, there are huge cross-sections for Z bosons. And it's not that costly to make them in association with quarks or gluons, which will turn into jets. So here's an example where a quark and an antiquark annihilate. There are a bunch of Feynman diagrams inside this blob, and you produce a Z boson along with these four hadronic jets. And then 20% of the time, the Z boson can decay to neutrinos. And when it does this, the neutrinos escape the detector, and it disappears, and it looks just like a pair of LSPs. So this is what we call an irreducible background. There's no way for the experimentalist to tell the difference except by understanding this precisely. There are many other backgrounds that are similar but reducible. In other words, if you make a mistake, it looks like MET plus four jets. So this precision theory and calculating to higher orders in the strong coupling constant can help with this. And so this is just an example of how sophisticated these supersymmetry searches are. What this shows is dozens of different searches, in this case with the number of jets along with the missing energy being 4. And they've also have similar plots, which I won't bore you with, for 1, 2, 3, 5, and 6 jets going along with the MET. And so every point here is where they have measured a rate, and they have compared it to their estimate of the background. In green is the reducible backgrounds in red, and then there's this irreducible background from Z to neutrinos, which is actually the biggest because this is on a logarithmic plot. So all these measurements, they agree with the background predictions, and they involve some theory and also some experimental techniques to determine them. But what you can see is that the number of observed is equal to the number of predicted everywhere they look. And there are hundreds of different sort of sub-measurements in here. So there are no excesses, otherwise you would have heard about it by now. And so instead of saying we've discovered supersymmetry, they set lower limits on the masses of the gluinos and other superparticles. So as an example, from the same paper, and CMS was able to make some exclusion plots that look like this. So they depend on both the mass of the lightest of the WIMP of the LSP and on the mass of the gluino. For example, if the mass of the LSP is very light, they exclude gluinos up to almost 2,000 GeV or 2 TeV. That's pretty incredible from a machine that's operating at 8 to 13 TeV because they're using up an awful lot of the proton's energy to make these particles, except they weren't actually making any in here. And there are various decays, so you can look at the vanilla jets that come from QQ bar. You can also ask if the jets have B particles in them, and then you can get slightly better reach, especially when the LSP is heavier. So that's just one example, and combining these and many other searches, there are a huge number of different searches that have been carried out. You can't even read this to know which one, but on the bottom here's the mass scale, and the mass scale corresponds to different kinds of particles. The gluino reach is typically the heaviest, but some of the other supersymmetric particles can be bounded for a while, out to hundreds of GeV. So supersymmetry isn't there, but it could still be there at slightly heavier masses. And the LHC is poised to collect much more data over the next couple of decades. So you should still watch this space. But at the same time, since there is no convincing evidence for supersymmetry or any other direct production of new particles, the other way to look for new physics is looking sort of closer to the standard model, looking for making measurements and looking for deviations in rates. And this can be the old particles of the standard model, or they can also involve the brand new Higgs boson. Studying its properties is going to be a big task of the LHC in the coming years. These measurements are actually a lot trickier than searches. You have to calibrate everything properly, and they take a while to perform. Also, they place more demands often on the theory to go to higher orders. So I want to show you some of the standard model measurements that have already been made by the Collider collaborations. Just happened to choose Atlas. CMS has very similar ones. And what you can see is that there's a huge range of cross-sections. Up here is the total cross-section for PP, and it's about 12 or 13 orders of magnitude higher than some of these extremely rare processes. So there's an incredible collision rate, and you have to actually dig out from under it to find all of these much rarer processes. But they include things like W's and Z's. Those are very large cross-sections. In fact, they've measured we were talking about Z production in association with 4 jets. That's this process here. It's been measured, and the blue is the uncertainties in 2015 on that rate, and they even measure down to 7 jets. And then the gray bands are the theory predictions. And usually theory is ahead of experiment, in that the theory bands are a little bit more narrow or more precise, but experiment is improving and theory needs to improve too. Over here is Higgs production. The Higgs has been seen, and this is its total cross-section, but that gamma-gamma rate I showed you, that's only part in 10 to the 3, or 2 parts in 10 to the 3 of the Higgs production. And so if you include this probability of going to gamma-gamma, it's actually much, much lower. There are other processes involving the heaviest quark. That's another place where new physics could be found. The top quark. They make millions of top quarks now at the LHC, so they can measure the total production rate rather precisely. And then there are ones that involve multiple electroweak bosons. At the time of 2015, mostly there were two-body final states in a double electroweak, like two Z's, or W and Z, or Z and photon. And there wasn't so much with larger numbers. But now the most recent measurements are really from 2019, and they include, well, they didn't bother showing all the Z plus jets anymore, but they are now measuring things with 3 electroweak vector bosons that have very tiny cross sections, especially when you take into account the decays of the W's and Z's to things that you can see well. And more things have been measured from the Higgs. Another way of producing the Higgs has been measured here. So now I want to turn a little bit from the experiment to the theory. And I want to talk about the framework we have for making all of those theory predictions. So at the core, the basic reason we can make such predictions at all is something called asymptotic freedom. When we study quantum field theories at different distance scales, we find that the coupling strengths depend logarithmically on the distance. In QED, if you are at distances much shorter than the Compton wavelength of the electron, you make electron pairs in the vacuum, and they polarize the vacuum and change the value of the QED coupling, which is called alpha, or 1 over 137, so that it runs with energy. The same thing happens in QCD, the theory of the strong interactions. The gluon self-interactions depend on a parameter called the strong coupling, alpha S. But they run in the opposite direction. There is a diagram, the gluon polarization of the vacuum, because the gluons carry charge themselves and have spin 1, it turns out that it has the opposite sign from the polarization effect of the quarks, which is the same as in QCD. And because of this opposite sign, the running is such that when you go to shorter distances, this coupling becomes smaller. When you have a small coupling, you can use perturbation theory. You can use things like Feynman diagrams. And so then the theory becomes calculable. At very small momenta or long distances, then the theory becomes extremely strong, and you can't calculate it very well except using techniques like lattice gauge theory. And in this regime, the quarks are bound into the proton. Over here, at very short distances, they don't see the size of the hadrons. Instead, they are almost free, and that's why we call it asymptotic freedom. This running is logarithmic, so it becomes very slow out here. So although it's running, this constant is roughly 1/10 at scales that the LHC is operating at. So once again, at long distances, things are confining. At short distances, they're calculable. At long distances, we have the proton itself coming into the collisions. Also, when the collision we can describe in terms of quarks and gluons, but as they emerge from the collision, they do so in jets or sprays of hadrons. At the end of the day, these quarks and gluons confine and turn into hadrons. We can't really predict this precisely, this confinement. We can just model it a bit. And this is the part that we can do more precisely. So to show this picture again a different way, there is a way to factorize or separate the problem into different pieces. And this is called QCD factorization, and it's strongly related to the parton model, which describes the structure of the proton in a particular way, that it's like a flashlight containing a beam of quarks and gluons. And whenever you have a suitable proton collision, you sort of sample one parton at a time, and you need to know a probability of finding these quarks inside the proton. But given a knowledge of that structure, then you can multiply those probabilities by another probability, which we call the short distance cross-section, to produce something, and there are certain restrictions on it. It should be something called infrared safe. But for example, the prediction of a Z, which you would see by its decay to E plus E minus, can be done in this way. So you have to take certain functions called parton distribution functions from experiment, and they're known to a few percent now through a lot of hard work. And then the theorist's job is to calculate this probability here, which is a sort of imaginary scattering process that takes place in the femto universe because it's at distances that are shorter than a femtometer, or 10 to the minus 15 meters. Actually, there's some arbitrariness where you draw this box, and that's called the factorization scale. So you might play with that a little bit to see how accurate your predictions are. And this box, this probability in here, we call it the short distance cross-section, and put a little hat on it. And we know pretty much all the standard model parameters that go into it. Alpha S isn't known perfectly, so it depends a little on alpha S. But it also depends on some artificial scales. This factorization scale is not a real scale. And there's also a renormalization scale. And so you can vary those a little bit to estimate the uncertainties in your calculation. Let me just, and the general thing you do is you expand the short distance cross-section in terms of powers of this relatively small coupling, alpha S, and it depends on what scale you evaluate it at. Depending on the process, you might have different powers of alpha S at leading order. I'm going to show you an example of Higgs production where this is 2, and then there are extra terms that come when you work harder and go to higher orders in alpha S. And as a result of combining these terms, you get more accurate predictions. So you might think that leading order would work okay if alpha S is a 10th, but actually these terms are very large, and you get very poor convergence until you go to higher orders. And depending on the process, you have to go to higher orders. This is essentially the worst case process, the production of the Higgs boson through gluon fusion, which we'll come back to at the end. But it depends on the LHC energy, so the later runs of the LHC have been at higher energy and have higher cross-sections. But this is the leading order prediction, and this is the state of the art next to leading order. And you can see that the leading order uncertainty estimate is not good at all. The actual answer is up here, nowhere near here. So you really need to go to at least NLO before you have any idea what the cross-section is. And at this point, you're still 20% uncertain for this. In some cases, maybe it's better than that. So anyway, the further you can go, the better prediction you can get. And all these cross-sections for the Higgs fold into our understanding of the Higgs properties and how it couples to all the other particles of the standard model. So to do that with precision, we really need to have these very precise predictions. So now under the hood, to produce these short distance cross-sections, I guess I should have put a hat here, sigma hat, they are a function of something we just generically call the S matrix. And it's not the supersymmetric S matrix. In the real world, it seems to be just the ordinary S matrix. But anyway, the answer is a function of S matrix elements. So we need to have tools to compute all these S matrix elements. And the first thing we need to do is compute the lowest order matrix elements. And those are what we call trees, because we can write down Feynman diagrams for them, and they have no closed loops. Here's a very simple tree which is for producing the Z boson in quark-antiquark annihilation, and then its decay to electron pairs. Now, there are also multi-jet production for gluons that require much more complicated trees with many more Feynman diagrams, but they're still relatively simple. And as you can see here, you can use textbook methods to study tree diagrams. But we want to go further. Trees only will give us the leading order cross sections, and those are really bad in terms of precision. So we need to go to next to leading order. And in order to do that, one of the ingredients we need are loop amplitudes. So here's an example of a loop amplitude, one loop. And this one is one of the ones that contributes to that background process I showed before, Z plus 4 jets. So this is where the fun starts, because using textbook techniques for loop diagrams like this is really too slow, even when you program it with computers. You need to reorganize things to try to make things much faster and more stable. So this is not the only thing you need for NLO. You also need to have tree diagrams with one more parton. So here is a loop diagram for this very simple process of Z production. But at the same order in alpha S, you need to square processes with extra gluons or quarks in them. However, these were the bottleneck for a long time, and we had to produce these in the early days in an artisanal way, one at a time. But now, through the work of many people, we know how to mass produce these loop amplitudes. Here's an indication of the challenge. If you want to produce, for example, a weak boson and N gluons, here are all the Feynman diagrams. And by the time you get to one loop and 3 gluons, you can't even resolve them on this plot. We were able to push these methods with Zvi and David and our collaborators as far as producing a W, this blue item, blue line, and 5 more jets. And the Feynman diagrams required for that were about 250,000, but we didn't use Feynman diagrams. We used another method, which I'll outline to you now. We actually went back to the 1960s. In the 1960s, QCD was not yet understood. There were many strongly interacting particles. People didn't know whether field theory would even work for this kind of problem. And so they were using more general properties. There was a bootstrap program based on the analytic properties, or what we now call on-shell information, because the only particles you put in are those that are external on their mass shell. And there was a lot of developments in there which they weren't able to make enough assumptions, and so they couldn't go all the way, but they had a lot of the right ideas. And one is that the basic properties of the S matrix are controlled by its singularities, just like singularities of functions in a complex plane. And the two kinds of singularities that you're used to in the complex plane are poles and branch cuts. The poles, in terms of the S matrix, correspond to regions where you can separate a scattering process into 2 processes that are almost disconnected. They're only connected by one light state propagating in between the 2 scatterings. And then there are branch cuts. Branch cuts arise when you have pairs of intermediate states, or maybe 3 or 4 intermediate states. In that case, when you move the scattering momentum from below threshold to above threshold, you get a discontinuity. It's a generalization of the optical theorem. Now, in fact, this analyticity fell out of favor in the 1970s once a Lagrangian for QCD became available, and people switched to Feynman rules. But eventually, to do more and more complicated processes, the Feynman rules became extremely tedious and cumbersome and not fast enough. And so we worked to resurrect some of the early ideas of analyticity and unitarity in order to compute these amplitudes in perturbative QCD for use at the LHC. Now, we had more information than they had in these days. We had underlying information about perturbation theory that could assist the analyticity. So one other sort of key philosophical point is that when you have a small number of Feynman diagrams, it's like having a small number of grains of sand in your hand. Each one does something kind of important, and it's useful to think about them one by one. But when you go to hundreds of thousands or millions of Feynman diagrams, they don't really mean much by themselves. It's more acting like a fluid, like if you were to pour the sand out of your hand. And so not thinking about it in terms of individual diagrams, but thinking of just how these blobs, which represent the sum of all the diagrams, move around, is a more practical way to think about things. There's also some miraculous zeros that happen in QCD at tree level, which we can exploit when we go to higher loops. For example, if we assign helicities to the gluons, it's been known since the 80s that if all the gluons have the same helicity, or just one of them has the opposite helicity, then you get exactly 0. And if exactly 2 of them have the opposite helicity, you get a very short formula in terms of some variables I won't bother defining, but there's an extremely short one-term formula that captures all of these very large number of Feynman diagrams. So when we use analyticity, we can recycle these simple formulas at tree level into simple formulas or fast evaluations at the loop level. So here's just a sketch or a little movie about how it happens. We want to take a scattering amplitude like this, and we want to do an analytic continuation of some type. That is, we want to change the kinematics smoothly and find simpler regions. So we move around in the kinematics, and then we discover some region where the amplitude falls apart into simpler ones. And maybe we already know what these are, and then we know the residues at this pole. And we can go find the residues at other poles by moving around in different ways. And when you carry out that picture, you get something called the BCFW recursion relations, which Lorenzo mentioned before. I didn't bother writing them down, but they basically write a complicated amplitude as a sum over products of simpler amplitudes. And they're recursive, so you can go from smaller numbers of particles to larger numbers. And it's all very straightforward. You can implement it very fast on it numerically too if you want. So these are examples of trees being recycled into more complicated trees. In fact, you can go down all the way to the simplest process. And the simplest process turns out to be 3 gluons scattering, which doesn't make any sense if they have real momenta, but we can have these momenta be complex and still be on shell to have p squared equals 0. And then this amplitude makes perfect sense, and it's really the building block, and it's totally unambiguous. Feynman vertices depend on the gauge that you choose and are sort of off-shell things, and you need 3 and 4 gluon vertices. But here, you only need this one building block. And so you can implement the BCFW recursion relations on this and get very compact analytic formulas or fast numerical results. And basically, you can do the same sort of thing at the loop level. You can take loop amplitudes, and you can deform the loop momenta here and split the loop integrands into regions where they factorize too. If these are 2 particles and real momenta, this is closely related to ordinary unitarity of the S matrix. But there's also a generalized unitarity, which is also recognized in the 60s, where you put more particles on shell. For example, you can take this left blob and split it up into 2 more, and these are what we call 3-particle cuts. So in this way, we can take these tree blobs and recycle them to generate loop amplitudes. The one thing that we had when we were doing this unitarity in the context of perturbation theory was a knowledge that the loop amplitude is actually a linear combination of certain loop integrals and certain coefficients. And we could compute these loop integrals once and for all, and then when we need a new process, we determine these coefficients using generalized unitarity. So this is a long story, and I'm only giving you a very brief part. There's also a piece called the rational part, which you need, and you can pick up quickly. But there were many programs that were developed around the early 2010s, and some of them have been refined and and more automation has been done. We specialized in vector boson plus multiple jets, getting very large multiplicities. Other groups had more automation involved. This one at the bottom, open loops, has been a very powerful program recently. But now we can use those and we can get predictions with quantifiable errors. For example, we studied Z plus 1, 2, 3, 4 jets at next to leading order. That's these Black Hat plus Sherpa plots. And you can see they agree quite well for the jet rates as far as we could go. There are some other approaches based on leading order plus Monte Carlo shower that do pretty well too. Their error bands are maybe not the same as ours. They're constrained a bit more. That is, they make certain assumptions when they produce these plots. But we can also predict many differential distributions, and they've measured dozens of differential distributions in many different processes. And everything is generally in pretty good agreement between theory and experiment. This is just a timeline that Gavin Salam put together to illustrate the progress that's been made at one loop, or rather next to leading order. And there was very little progress for a while until around 2006 or so, where people were able to go to 2 goes to 4 through 2 goes to 6 and develop, along with this, a large increase in the number of different processes. So I guess I have maybe 5 minutes left or less? 10 minutes, okay, great. So that was all about one loop. And a lot of the developments in one loop sort of, they're still going on, but there was a big period around 2011 to 2013 where a lot happened. So the next frontier is to do the same thing at 2 loops. And with a couple exceptions I'll get to later, the state of the art is mostly stuck at 2 goes to 2. And the problems for 2 loops are not exactly the same as the ones for 1 loop. At 1 loop, I showed you that there was just a finite set of 1 loop integrals, and they could have been done in the 70s. They're more or less all done and all known. But at 2 loops, different processes give rise to integrals that are either simpler or sometimes very complex. And so a lot of the issues have been in trying to understand the 2 loop integrals. The 1 loop case, everything, the worst integral you ever get is what we call a scalar box integral with 4 propagators in it. And those were known since the time, at least, of 't Hooft and Veltman, to be all expressible in terms of logarithms and then one special function called the dilog. In contrast, the 2 loop ones involve certain polylogarithms and even things that are more difficult called elliptic polylogarithms. For example, at 2 loops, if you have massive particles everywhere, then even this very simple looking integral, which we call the sunset integral, which has 3 massive lines here and a generic momentum coming in, that one is not even a straightforward generalization of the dilogarithm. So it's called elliptic. And although there was numerical work on it a long time ago, and that numerical work is suitable for some applications, there's a lot of interest in understanding analytic properties of integrals related to this. For example, this integral appears when you want to compute top production at next to leading order. You get diagrams like this, and these integrals are related to integrals where you cancel out some of the propagators. If you cancel these propagators, you can contract those lines, and then you can see it looks like a sunset. So this sunset is hiding inside top production. Now, top production is already known, TT bar production at NNLO, for about 7 years. It was done numerically, and so that was adequate. But if we want to go to TT bar plus jet, now we have a much more complicated phase space, and we need a better analytic understanding. So that's an example of some of the frontiers to go to next to leading order. There is a class of processes like W production, which is dominated by massless lines. When all of these lines are massless, then the integrals can be done in terms of multiple polylogarithms, which are more straightforward generalizations of the dialogues. And that advance around 2011, 2012, people were able to compute quite a few of these processes, two-loop amplitudes, and that generated a large class of 2-to-2 processes in an LO. So I showed you an NLO timeline. Here's a NNLO timeline, which is even more detailed and having many specific processes in it. But what you can see, if you could read these here, all these processes up here are essentially 2-goes-to-1 processes. And those were much simpler. So the advances in doing these two-loop integrals allowed the computation of many 2-goes-to-2 processes. So the next barrier is to go beyond 2-goes-to-2. In order to do that, for 2-goes-to-2, you could get away with using Feynman diagrams, but to go beyond that, it's much more efficient to use multi-loop generalized unitarity. There's a lot of progress that I have no time to review. And also you need these very sophisticated methods for multi-scale, multi-loop integration. But if you look at this, this construction here, you know that trees can be recycled into multi-loops with a little work from your friendly arborist. So the state of the art now is that the first two-loop 2-goes-to-3 amplitudes are being computed, and there was a lot of work over the last few years, especially their analytic formulas for all the cases for pure QCD at the leading order in the number of colors. And those were carried out by a number of groups, but especially the most complete calculations were done by Abroy, Dormans, Febres Cordero, Ida, Page, Zung, and Sotnikov. Now, those are the two-loop amplitudes, but not yet the NNLO cross-section. That is has a lot of other methods that have to be refined to get those cross-sections out. There is another case of 2-goes-to-3, in which it's much simpler to go from the amplitudes to the cross-section, and that's pp to 3 photons. And that was recently carried out by this group, Chaudhry, Chacon, Mitov, and Poncelet, again in this large N limit. And what you can see here, these green guys are all basically leading order, never mind what the different points were. And here's next to leading order, and here is next to leading order. In this case, the expansion is also very badly behaved, like Higgs production. But by the time you get to next to leading order, you can see that the results are in the ballpark of the measurement from Atlas. So I think this is a real triumph for NNLO beyond 2-to-2, but we'll see a lot more of it as we go forward. I'm going to skip through this for lack of time, but this is just describing a little bit more about how you could do, how Higgs production was done all the way at NNLO. So I'd like to conclude by saying that we've seen a real revolution in how precise theory we can get for QCD, the underlying physics at the LHC, in order to compute very important hadron collider processes at NLO and NNLO, and even now in some cases at NNLO. This is far beyond what people thought was possible 20 years ago. So it required a new understanding of scattering amplitudes at a formal level and all their analytic properties, as well as some efficient and stable implementation to get the numbers out. And many people, many groups contributed to this progress. In parallel, there's been a lot of progress in understanding amplitudes in supersymmetric gauge theories and also in gravity. And I think later today we'll hear more about that latter topic from Svi Byrne. So this sort of revolution in our understanding of QCD is far from over. There are many, many more processes that await, and we also look forward to all the data that will be produced by the LHC in the coming decade. So thanks a lot.
Okay, thank you very much for this very nice talk. We have time for questions. One by one.
Nobody wants to ask the first question. Maria Elena.
Hey, hi. So it It's a very nice talk. What do you think about working in parallel in the following sense? You have an experiment that needs your theoretical predictions, and at the same time you want to learn about the fundamental things of the S matrix, the amplitudes at all orders. So sometimes there's no time. So you as a theorist, you get requested these amplitudes at a fixed order, but at the same time you have interest in going beyond and looking at all these nice identities and connections. So for the younger generation, what would you say about this? How would you invest your time?
Well, you really have to choose what is most interesting to you. I balance my time a bit, but every now and then I take a vacation from the real world and I go off and do planar n=4 super Yang-Mills theory because it's much more fun. And I even try to suck respectable phenomenologists off into that direction sometimes. And sometimes we learn things and it comes back. But it is a tricky question. As this field has grown, this field of scattering amplitudes, there's an annual conference, which like Lorenzo's been to, and I think it's grown even faster in terms of numbers of people, off in the more formal directions. And I want to try to keep them anchored to the real world somewhat, at least. Well, there's actually two real worlds. There's the LHC real world, and Zvi will probably talk about the LIGO world, because there are also some connections to data in that direction. But when you're young, you have to kind of pick and choose. So it's good to be T-shaped. That is to say, it's good to find an area where you can specialize and drill down deeply. But it's also very good to keep some knowledge across the field, so you can be thinking about where the things you know might be applied somewhere else.
Okay. Some other question? I have one question on something that you touched shortly. And I think you said that you don't need for doing in this unitary part like the ghost.
Yeah.
So in the 80s, in the 90s, in the textbooks where we learn field theory, it was said that we have these different gauges for doing calculations, and the unitary gauge was like non-renormalizable. But I see that in these methods you go to loops. So how is that? Can we have a unitary gauge that is renormalizable?
Well, we're not trying to calculate generic off-shell Green's functions. I think that's probably where the answer lies.
Oh, okay.
That the non-renormalizability would matter if we really wanted generic off-shell Green's functions. But when you go on shell and you just restrict to the physical states, you can get back all the things that you wanted to get or that you got with textbooks and ghosts. So in the textbook calculation of the beta function, the ghosts play a critical role. But there is no reason to do it that way. But you have to do something slightly different. You can do an on-shell calculation that has buried within it the ultraviolet divergences for the beta function. However, it has mixed into it infrared divergences that have to be disentangled. So once you understand the infrared divergences, which are actually related to tree calculations through the overall cancellation of all infrared divergences, you can get the beta function out of an on-shell calculation with no ghosts at all. And so the non-renormalizability never shows up. And I think it's basically because it affects only off-shell Green's functions.
Okay.
Good question. James?
So thank you for a very interesting talk. At one point you mentioned the spinor helicity formalism, and you mentioned obviously the maximally helicity violating amplitudes. But in traditional settings, the spinor helicity formalism was developed for particles which have zero mass. More recently, there have been some generalizations that can take into account fermions with non-zero mass. I was just wondering whether the techniques that you mentioned are able to be generalized and applied using spinor helicity for massive particles.
Yeah, that's a great question. There were spinor helicity methods for massive fermions in the 80s and so on, but I think the work of Nima Arkani Hamed and Yutin Huang and collaborators was a little more elegant way of putting it in terms of quantities that transform nicely under the massive little group. And those sort of give you the external handles that you need in order to, or they help you in trying to use unitarity. And most things go through pretty well with massive particles, but there is one additional subtlety. When you have only massless particles, you can ignore certain classes of contributions, which are called bubbles on external legs. And those are rather singular because if the external particle, you want it to be exactly on shell, then this internal propagator that connects you to the bubble will also be on shell and it'll be infinite. So you have to figure out a way around it. Now, if every particle going around the loop is massless, like it was in everything we did, then that bubble integrates to zero. So the fact that you don't know exactly what its integrand is of no consequence. So other groups have been able to handle things with massive particles in them, but they do something slightly different. They have for example, there's a method called the OPP method, and it's not quite as on shell as what we do, and what they do is they do get some gauge dependence in certain terms that allow them to get this. It works fine numerically, so it's not like it's a problem or anything. More recently, there have been some discussions of how to do this in a completely on-shell way by Brito and collaborator in Simon Badger more recently. I haven't studied them in detail, but in some sense, you have to go slightly off-shell. You have to kind of take some derivative in some variable in order to handle these massive external bubbles.
Okay, thank you very much.
Sure. Question?
Albert.
Sorry.
Hi. You mentioned that in spite of the fact that the coupling is a tenth, you actually have very poor convergence properties. So you need to go to a rather high order. Now that means that the numerical coefficient in front of your powers at 1/10 is larger than you would expect. Yeah. Or naively expect. So my question is, how do you know ahead of time what a decent estimate of that coefficient is, to know how high an order you need to go for the particular process? Is that your estimate on the basis of how many Feynman diagrams you have, or?
There are some hand-waving arguments you can make. They're not very good, but you can kind of estimate them. I mean, oftentimes there are extra logarithms of explicit scales or maybe some implicit scales that show up. One case where you know and you can see that there are large logarithms is if you produce something like the Higgs boson at finite transverse momentum and you try to take that momentum down to zero, you can just see that there are large logarithms of the ratio of the Higgs to the momentum. And that's called a place where you know that you have to sum up those logarithms. That's called PT resummation. But there's also a similar resummation that's a little bit more hidden in the longitudinal direction called threshold resummation. And it has to do with the fact that when you have two gluons which have a large color charge, they come in and they annihilate to a Higgs which has no color charge. There's a huge amount of sort of breaking radiation, Bremsstrahlung, of gluons that are emitted. And those gluons cause a little mismatch between real and virtual and cause the terms to be large. And so based on the idea that you have large color charge coming in and nothing coming out, you can understand sort of why the correction should be large. But that's just one class of cases where the corrections are large, and I'm not saying you can understand everything that way. But in some cases, you can get some intuition. Sometimes it only comes after the fact.
Okay, if there are no more questions, let's thank again Lance for the very nice talk. So actually we are a bit ahead of time, so we have the next talk will be by María Elena, so we'll proceed. María Elena Tejeda-Yomans from Universidad de Colima, and she will talk about amplitude and XQCD.
Right. So it's really nice to be here. It's the first time speaking from this place. It was more than 20 years ago that I was here as a student in one of these national schools learning about group theory in low energy nuclear physics. So it makes it perfect for me to talk about what I'm talking now. So I'm going to be discussing QCD as a continuation of what Lance was talking about, but then I'm going into sexy QCD, extreme QCD, which is the study of the interactions of quarks and gluons, but in a medium, and with lots of things happening. So hopefully I can fit that in the time that I have. So as Lance was saying to you, we have a very nice gauge theory, QCD, that provides us with a regime in which we can calculate many things, a perturbative regime. And this theory is built upon many, many years of data. And now, as Lance has summarized, it provides us with many handles to calculate predictions for current and future experiments. So it's really nice that for me, in the years after the 80s, that the field has flourished and it has many, many nice predictions for the LHC and the current experiments. Now, QCD is interconnected with many QCD cousins. Let's say you can think about PQCD, perturbative QCD, as a whole field in itself, where many, many of the topics Lance was discussing are connected to, let's call them in general, perturbative techniques, but there's also the corresponding non-perturbative regime of QCD, where you use also really nice methods, numerical implementations, and all orders integral setups like Schwinger-Dyson equations to try to describe hadrons. And then there's also like a collection of versions of QCD that help study concrete phenomenology in different settings. So I'm going to focus on one of these versions. Let me start by telling you about how the things that I learned from regular QCD help me in the work that I do now in extreme QCD. And I'm going to pick up on the topic that Lance mentioned about QCD factorization. It's a really powerful idea, the idea that if you want to describe an observable, let's say, if you want to describe the structure of the proton in deep inelastic scattering, it's a really nice idea posed by several people here in the late 80s, that this observable that you want to measure at the level of quantum field theory, you can show that let's say the cross-section for hadron production in deep inelastic scattering is actually a product of probabilities, a convolution of two objects. One of the objects is this Parton distribution function, and it's actually universal. And the other object that Lance was talking about has to do with this sigma hat, this theory input of the heart cross-section. So the fact that we have this kind of factorization theorem helps a lot in all of the things observable-wise, well-defined observables for current experiments. Now, even today, even in recent years, this idea of QCD factorization still helps to produce universal PDFs in different settings, not only for the LHC, for many experiments. And typically, we would have an algorithm where we determine these PDFs, let's say from lepton-proton collisions in DIS, and given their universality, we use them as a given to a certain extent to do predictions for the LHC, let's say, W prediction in proton-proton collisions. And the fact that we can do this, the fact that at the level of operational construction of predictions, we can actually use these objects here, it's sustained or is built upon these factorization theorems. So let me go a little bit in detail about what we mean about this QCD factorization. In hadron-Hallon collisions, actually this cross-section that you want to measure, to observe, you pose the following idea. You say, okay, I'm going to take all of the physics that happens at short distance in one of these functions, and then all of the physics that has to do with this kind of universal radiation for the external states goes into this long distance function. And I'm going to be careful because, as Lance was saying, it's a non-trivial where do you set this boundary between short and long distances, and it also has to do with the fact that this idea of factorization is an approximation. It actually works rather well when the transfer momenta is really big, because this idea of factorization has these corrections of the inverse power of that momentum. But in the setting of the LHC, what happens is that these are really tiny, and then you actually have almost like the perfect setting for your calculations, because you can focus on the short distance physics theory-wise with quantum field theory methods, and then you can leave the long distance physics to a worldwide fit to get these PDFs or fragmentation functions. And when you do that, and you don't take into account this term here, and you realize also that this separation of long distance and short distance physics is actually of your own choosing, it's arbitrary, then you must implement the fact that this separation of physics is arbitrary, so therefore this observable must not depend on where do you choose this separation. I'm just being broad in this conversation, but to summarize, the fact that this object doesn't depend on this decision actually makes it so that the short distance physics function and the long distance physics function are connected through a very nice function that collects all the let me say, organized way the quarks and gluons radiate. And it's really nice because then at the level of the theoretical level, it means that the observable is actually like an exponential of these objects. And it makes it nice not only at the theoretical level, but also at the practical level when you want to simulate and build Monte Carlos to predict these kind of observables. And these two ideas, the ideas of evolution and resummation, or these sort of equations that connect these two functions, are actually nothing more than to ask for boost invariance and scale invariance of the whole premise of the whole setup of factorization. So Given that I went into this topic of factorization, let me tell you why this is still relevant for the area that I'm working on now. And I'm gonna just go a bit faster on this because Lance just went through this. In the 90s, people were working on different kinds of Feynman diagrams that contribute to all these cross sections for the LHC, and by the by the 2000s, early 2000s, we were working on these two-loop integrals that are relevant for 2-to-2 parton scattering at the LHC. And the fact that we were going about it in a sort of practical way rather than in a succinct way made it so that we realize that our calculations at a fixed level in this kind of topologies were telling us things about the way we should write the way that we should collect the information regarding how these partons in a 2-to-2 scattering would radiate. And we only realized that after the fact, after we perform all these calculations. Historical-wise, the way that it worked, as Lance nicely summarized, is that once people were doing all of these fancy higher loop calculations, then it influenced the way people discussed many branch tree Feynman diagram, these ideas that Lance summarized. So back then, if you wanted to get a 2-to-2, the interaction of two partons in a Hadron Collider, then we had to figure out some algorithm where you calculate Feynman diagrams in a setting, and you identify the main ingredients of this calculation through these integrals, and then you collect information in a way that you could isolate the infrared divergences, ultraviolet divergences through an epsilon expansion. And back then it was done in this way because we were preparing to provide this information for the people who were building the Monte Carlos for the LHC. But we also realized that our results, this kind of crunching down of lots of calculations, these results could also be written in a more physical way based on the work that was done by Bernd Gille and Catani and Seymour regarding the fact that actually these divergences should be explained in terms of how partons radiate and the fact that these partons radiate in color space, lose color or earn color as they radiate. It makes it so that we identify our results in terms of operators that work in color space that contain all these soft and collinear singularities, or that can provide like a sort of like an antenna function that gives you the way gluons radiate. And we could do it back then for one loop calculations and also for two loop calculations, except we could leave it at the level of an organized manner to report our results and to understand how we could compare with Lance's and other people's results. But somehow the fact that we are doing these calculations and that we are getting the information of the radiation in terms of poles means that we should be able to understand those in terms of this factorization of amplitudes in QCD. So let me tell you a little bit about that. If you think about a 2-to-2 parton scattering and you look at the amplitude of this process, which is in color space, I'm not going to spend a lot of time in this technicality. George and I were thinking, how can we start from looking at the fixed order calculations and see about the factorization of this amplitude, not at the level of the cross-section, but at the level of the amplitude. And we proposed, again, a separation of physics, where now we have a process-dependent function that has all the short-distance physics again, which is identified as a hard scattering matrix, which also can be calculated. And then two interesting functions, one that has, let's say, all the coherence of radiation, all the radiation that can probe the color space around the partons as they radiate, and then a function that actually collects all the universal ways in which the partons radiate collinearly, and it's all of them described by this evolution. So in the end, again, if you argue that this object doesn't know anything about your choosing of factorization, you end up with exponentiation of the way this amplitude behaves in terms of convolution of the information between several orders of distance in physics. This led us to report that we could understand why the fixed order calculations we had performed before had this particular set of poles, because now we could see that all the contributions from these poles actually come from the soft part or the hard part or the jet part, and we could check that that works even at 2-loop level or beyond, 3-loop level, etc. And once we did that, then at that point, it was fine with me in the sense that I had already done all these calculations, and then now I can understand why I saw all these patterns as I was doing those calculations, because all the Feynman diagrams, all the integrals collapse down to this kind of very nice operator, radiation operator that acts on color space, and they give you information to all orders in loops for these kind of amplitudes. So I think for me, the study of factorization at the level of the amplitudes gave a whole lot opened a lot of doors to question what happens to loop amplitudes at all orders, and in terms of finiteness, connection to other dimensions, and in other theories as well. And this is still happening now. People are working on form factors, many loop splittings, etc. And they are still reporting in terms of this language, where we now have a way to accommodate where the radiation comes from and how it is prepared to be canceled with other contributions. Now, that was regarding the experience that I had with amplitudes with QCD. So now I'm going to try to tell you about how this experience permeates to this new area that I'm working on. Let me tell you about extreme QCD, just tiny historical details. Even just right after QCD was established with asymptotic freedom and infrared slavery, with this seminal work by these guys who won the Nobel Prize, just right after, people were actually wondering whether we could have quarks and gluons under pressure, under high densities situations, under a high temperature state. What would happen with all the nice properties of QCD if we set about to study this kind of phenomenology? And just simple number of degrees count can give you basic thermodynamic properties for this kind of situation in which you have quarks and gluons, let's say, confined in pions, if you have a pion gas, or if you have them in sort of like a free state, you have a gas of quarks and gluons. Already these simple thermodynamical ideas give you quite different sizes for thermodynamical quantities such as pressure. And it's Even now, we have lattice gauge theory, this area where you have numerical implementation of QCD, that they can actually build the thermodynamical properties of this gas of quarks and gluons, and you can actually see that pressure, energy density, entropy of these gases, of quarks and gluons, of QCD in an extreme environment, behave in a really interesting way. You have a critical temperature under which these quantities grow quite a lot. So you have phase transitions and models where you can try to describe this situation with only hadrons that you know from your PDG book actually don't work very well beyond a certain temperature. And these are very nice things that I don't have time to review. So extreme QCD is actually QCD, let's say in equilibrium at a certain temperature, and considering a certain number types of baryons in this system. Besides the already intrinsic scale of QCD, you have, of course, a new scale that has to do with the temperature and the chemical potential now that you assume in this new system. So regular QCD, QCD in the vacuum, already has certain scales that we have to deal with. But now you have to imagine that we have competing scales for QCD in medium. And the question is, not only can we use quantum field theory to predict properties of quarks and gluons propagating in this medium and try to understand the phase transitions and the symmetries that are broken when this happens, but do we have the machines whereby we can have observables so that we can check our predictions? So typically in this area we are looking to provide a precise determination of what would the QCD phase diagram would look like. What does that mean? It means QCD matter under temperature and under changes of temperature and chemical potential. How does it look? Do we have at low temperature and low chemical potential, do we only have like a hadron gas? What happens if we do a high temperature experiment? Do we have a phase transition? What do we have there? And if we don't do an experiment at high temperature and we just compactify or put under pressure this QCD matter, what do we have then? So the theoretical community in this area has provided many, many predictions for this phase diagram. And currently, there are several experiments that are trying to provide data so that theoretical predictions can be compared with this data. And this is just a schematic diagram where you have the same phase diagram. This is the temperature, and this is the chemical potential. And if you start with protons and ions, regular nuclei, let's say cold matter, and you collide them in the LHC or RIC, then you're basically taking nuclear matter and putting, making it transition through a path in this phase diagram that goes parallel to the temperature axis. But if you use other machines that are currently planned, then the idea is not to go really high in temperature, but rather to try to generate a high density state at a fixed temperature and try to scan what happens to this same hadron matter if it goes to the same, if it goes through the same phase transitions or if we can learn something about other transitions such as the chiral or the deconfinement transition. So, the purpose of my talk is to try to, how much time do I have left? How many? Okay. Is to say that, of course, factorization works to a certain extent in the vacuum for QCD, but the question is, what happens if we now have ion collisions, even though we know that the leading part of this factorization structure works very well. What happens when we look at the subleading power of these hadron observables, what happens if we change the object that we're colliding? Can we still get away with factorization at the cross-section level or the amplitude level? One of the tools that we use to learn about this is jets, as Lance was talking to you about. In the medium, when there's the so-called quark-gluon plasma created, instead of having the back-to-back jet signal, you have this quenched jet, this jet that has to go through the matter, and it's actually suppressed when you look for it. And this is the reason that this jet is suppressed, or these kinds of signals are suppressed, is because this matter, this quark-gluon plasma, is formed of quarks and gluons that make it so that the parton that is created at the hard scattering, it has to travel through this medium and has to interact, has to have multiple collisions, has to leave energy in the medium, but and so that it makes it so that this jet is quenched. So the jets are still our preferred signal to study this system, but the quenching of the jet carries information of the medium, actually, and it can help you characterize the properties of this medium. So when you have a high PT probe, factorization is still used, ignoring the corrections. We can still do the separation of scales. And you can think about now, if you have collisions, ion collisions, you can say, well, just do what you know how to do. You just factorize your cross-section. And instead of having your usual PDFs, just use some scale PDF where you now have many protons in the incoming state. So all the physics should be scaled by the fact that you now have many protons collisions. But when you look at experiments, actually for these ratios of observables in ion-ion collisions and versus PP collisions, such as the yield, what you find is that there's a non-trivial dependence in PT. There's no direct scaling of the fact that you now collide many protons instead of just bunches of protons at the LHC. You can see that also for, this is dying. You can see also for single inclusive jets, for example, at Atlas, at the LHC, you can see that if you collide ions, these are lead ions, the suppression of the jet depends on how the ions collided in terms of centrality. So the information that you want to get through jets is there, except now you have to sort of correlate with the fact that you have a bigger system to begin with, and factorization ideas have to accommodate this. Now, how can we start about building a framework in which we can still work with factorization but in a medium? Well, this was work already done started many years ago. Gross, Pisarski, and many other people have continued that work, in which you consider a system of quarks and gluons that are in a thermal bath, but where, this is a key point, where the temperature is actually the biggest scale of all the processes. And in that context, you have a methodology, which is called hard thermal loop approximation, in which you can actually construct the amplitudes in these gauge theories, hot gauge theories, and you can still separate physics now in terms of the leading temperature contributions and sort of the soft momenta that is regulated by the coupling. So you can still have all your resumation and evolution if you make a decision of the hierarchy of the scales, and the temperature is the biggest scale. Let me show you, for example, this is the one-loop endpoint gluon function in terms of the amplitude of a tree amplitude. Only the thermal part, the leading temperature part, is actually very nice. You can factorize the operators, the statistical operators. And so there's a framework for the leading temperature results that collects or has the spirit of what we already saw in vacuum. There's actually work also by Brandt, Ashok, all these people recently, well, in the mid-2000s, where you can build an effective action and build an operator that brings out this collection of leading divergences or leading contributions in using this thermal effective action. And again, if you write an endpoint thermal diagram now with finite chemical potential, again you have, let me call it a factorization of terms that involve amplitudes at zero temperature. And this, again, this formalism, I don't have time to go into it, but it's also showing potential on what we could do for a factorization procedure in medium. So, one more minute, or no? 2, thank you. So, to make matters nicer and sexier, because they were not as sexy before. When you have an ion collision, there's another fascinating thing that happens. Actually, when you collide ions, and these guys are not coming in face to face, but they come with a certain impact parameter, then you have a whole bunch of charge that is flying away from the collision point. So you have like currents, and when you have currents of charge, you have magnetic fields. Well, it turns out that at the LHC and at the rig where these experiments have been performed, these electromagnetic fields are the biggest human-made electromagnetic fields in the lab, and actually they matter, for example, for photon production in these collisions. So people, as in our group as well, we are trying to build a complementary sort of phase diagram for QCD when there's also a really intense magnetic field present in the system. And wonderful things happen. One of the wonderful things that happens when you have a magnetic field, intense magnetic field, is that you have an opening of channels that you didn't have before. You know that there's a prohibition of, or there's a null result when you want to calculate this 3-point function, and you take them all into account, that this should be equal to 0. But when you turn on this really intense magnetic field, this channel opens up. So you can build, let's say, a formalism using these basic quantum field theory techniques to provide information on how does the, let's say, the alpha S, how does alpha S looks for the quarks and gluons that live in these moments where the collision is happening, and how does that influence observables? I didn't write the observables? Yes. So for example, we can calculate how many more photons would you produce if you have these intense magnetic fields at the collision. And these are basically calculations that are based, again, on ideas of factorization, but in an artisanal way. So the work that I want to do now is take these ideas that I've gone into with different collaborators and maybe put them together to try to have a coherent program for factorization, QC factorization in medium. So I'm just going to leave it like that. This is the outlook. So thank you. This is dying. Esto está muriendo.
Okay. So, time for questions? Over there.
Okay, I didn't understand what's the fundamental argument behind the factorization. I mean, you have a term that is the convolution of high energy physics and a term that is that has the low energy physics. What's the fundamental argument behind this?
Well, that's it, pretty much. Well,
I mean, it is supposed that high energy physics is not related with low energy physics.
No,
but
well,
from this point of view, it seems that it does.
So one of the key points to make when you want to factorize in QCD is that you are thinking of the proton coming in at a really high energy, and you are thinking that when they interact at the collision points, actually they're coming in at such a high energy that, as Lance was trying to say, quarks and gluons in them are the actual the actual objects interacting at really short time in this collision.
Okay, but that's high energy physics,
right? Quarks and gluons, right? But these quarks and gluons actually, when they interact, they fly away. It takes a long time for them to fly away, and when they're flying away, they start to radiate. And somehow this idea needs to be connected with the fact that at the detectors you have bunches of hadrons, these jets, right? So this is after a really long time compared to the time where this hard scattering happened. So you're trying to, this that I'm saying, you're trying to put it in this framework in which you say, okay, I'm going to think about this process as a quark and an anti-quark coming in, interacting and producing, let's say, a gluon and another gluon. And then I'm going to put in that information in this, in this blue object here. And I'm going to think about how these quarks and gluons live in a color field that actually makes them radiate between themselves in the initial state and the final state. And then separately, I'm going to think about how one quark, when it travels in vacuum, radiates and becomes a bunch of hadrons. And that's the red object there. So you're sort of compartmentalizing the problem.
Can you derive this relation from fundamental arguments, I mean from the theory? Or this is just an assumption? The factorization?
Well, that's kind of like a tricky question. Okay. Fundamental arguments.
I mean from the theory, from the technical
I would say
tools
yes.
of the theory.
I would say yes, but it would mean that we need to organize like a 5-day workshop on this.
Okay. Thank you for your nice
presentation. No, there's people like Sturman, Soper, and all these people in the 80s that build a theoretical framework under which you can write diagrams, like complicated diagrams, and sort of cut them up, fraction them up, to separate what is really long distance and short distance, and sort of build this or give support to this idea. But it depends on how you think about fundamentals, I think.
Okay. Salim?
Okay. So in one of your early slides, you had something about new physics in the short distance amplitudes.
That's the new physics for me that's there. I needed to write new physics somewhere.
But the question is does this prefer is there any particular new physics that could be discovered preferently in extreme QCD or this kind of experiment?
In extreme QCD or in general? Where is this slide? I think it's somewhere here, no? No, in the factorized. Anyways, let's say, when Lance was explaining, for example, this observable, what was it? It was protons coming in, producing these gluinos, and then having some signal where there was some missing energy. So in principle, the new physics that I mean is that at the theoretical level, you could have your Lagrangian of whatever ingredients, and you could calculate this object, and then use factorization in QCD to get a cross-section. That's no problem. That's what people do all the time with these Monte Carlos. So in principle, you could use, like Lance was summarizing, you could use all these missing energy signals to look for new physics, right? But in practical terms, this is again built upon factorization in QCD. You have a cross-section, you have quarks and gluons that you can see as jets, and then some other guys that you cannot. But still, what you did is you did some partonic level cross-section, no? And that's what in practice it's done. To look for new physics, you look for this kind of missing energy signals, for example.
Okay,
but you needed to have the theoretical. Now, in extreme QCD, what we're trying to do is we're trying to find, so new physics in extreme QCD implies that we find theoretical predictions points in this phase diagram. So you need to find phase transitions, or you need to say, if I count the number of protons or the number of pions in an event, and I see a fluctuation of this number, then this is an indication that there's some change in the system that was abrupt. So at the level of the observable, again, you use this kind of factorized structures to calculate yields of particles, and then you wait for the data to show if there's some fluctuations, things like that. That's the equivalent of new physics in that area.
Okay, thanks for that nice talk. Can you say a little more on the experimental side about how these other machines like FAIR would move further to the right in the phase diagram?
Right. So this is a very important issue because traditionally when we listen about the ion collisions at the LHC, we have gold or lead, in that case, ions that go very fast. And so we have a scan of the RIC and the LHC, the first phase of the BESS scan and the LHC that goes very parallel to this temperature axis. And it was very nice because you can verify that there's, after this theoretically poised critical point, there's not really a phase transition, but some kind of smooth transition between the two phases. But the theoretical predictions show that there should be some critical point somewhere there, and the chiral transition and the confinement transition should somehow meet in this critical point. And the only way to probe is to think of a machine or think of an experiment where the scan can go this way and that way. So FAIR and NICA, FAIR is in Germany, and NICA is in Dubna, in Russia. What they thought about is to, instead of colliding these nuclei at such a high energy, you lower the energy and you use a range of ions from lead down to copper, carbon, all these. And what you achieve is that you have like a stopping, it's called a stopping effect. When these ions meet, since they have many protons in them, actually what happens is that you have, there's a time in which the density grows before going into the sort of regular way that the system evolves in these other machines. So in that sense, NICA and FAIR are crucial if we actually want to learn about the, and RIC BESS2 actually goes, it's not, it is there, the purple line there, the second round of RIC BESS2 goes down and overlaps with the theoretically critical point. But these two machines are actually the perfect machines to learn about these phase transitions. Otherwise, you couldn't access that with the LHC. And there are proposals, I've been told by the local ALICE community in Mexico, there are proposals whereby they could prepare special runs at the LHC where they can actually try to complement what the other two machines are doing. But it's really hard because the LHC is a high energy dedicated machine. So in the new physics, sort of in the quest of new physics, we are actually, myself, I'm involved in NICA MPD project here in Mexico, where we now do theoretical calculations for this machine. And hopefully it can start colliding gold ions at 11 GeV, 4 GeV, 9 GeV in about 2 years. So hopefully we can report on that.
So is that GeV or GeV per nucleon?
Per nucleon.
Yeah. Thanks a lot.
Thank you.
Okay, so we'll stop here. We thank Marilena again. So we are now on time. We don't need to renormalize time, and so we'll return at noon flat and to continue with the next talks. Thank you. Muy bien. Bueno, pero ustedes fueron sortudos de ahí de tiempo para las preguntas. Oye, no sé, ¿me ayudas a moderar las que siguen?
Sí.
La siguiente 3.
Sí, es Roger,
Mauro.
Have been destroyed by Spartacus.
Spartacus, a motion picture unequaled in the entire history of filmmaking, unlikely ever to be surpassed. In the tenderness.
Soy Leonardo López Luján, miembro del Colegio Nacional, y quisiera invitarlos a todos ustedes a asistir al ciclo de conferencias La Arqueología Hoy. Para este año de 2020 hemos preparado un riquísimo programa en el cual invitaremos a los protagonistas de la arqueología para que nos hablen de sus descubrimientos, no solo en México, sino en otras áreas como Guatemala, Perú y España. Hemos elaborado un programa muy interesante que irá desde las cabezas monumentales olmecas hasta los vasos funerarios hallados en las pirámides de las selvas mayas. También abordaremos la última tecnología que se aplica en la ciencia arqueológica. Entre otras técnicas, se platicará acerca del LiDAR, de los drones y cómo estas técnicas contribuyen a un mejor conocimiento de las civilizaciones antiguas. Las conferencias tendrán lugar en el aula mayor del Colegio Nacional, aquí en la calle de Donceles, en el Centro Histórico de la Ciudad de México, y la entrada es libre. Los esperamos a todos. Muchas gracias.
Cualquier pretexto es bueno para visitar el centro histórico de la Ciudad de México. Hay edificios maravillosos, rincones que usted jamás ha visto. Y desde luego hay sitios que son de visita obligada. Me refiero al Colegio Nacional. Un espacio donde se junta la inteligencia, la imaginación, el arte, la ciencia y algo muy bonito, la conversación y la amistad. En este edificio hay ahora un nuevo espacio. Es luminoso, es grato, es agradable y está el mejor amigo de usted, mío y de todos nosotros. ¿Sabe qué es? Un libro, muchos libros, una historia, muchas vidas que van a enriquecer la nuestra. Vengan a visitar la librería del Colegio Nacional.
Sí, me parece lindo.
have been destroyed by Spartacus.
Spartacus, a motion picture unequaled in the entire history of filmmaking, unlikely ever to be surpassed. In the tenderness.
Soy Leonardo López Luján, miembro del Colegio Nacional, y quisiera invitarlos a todos ustedes a asistir al ciclo de conferencias La Arqueología Hoy. Para este año de 2020 hemos preparado un riquísimo programa en el cual invitaremos a los protagonistas de la arqueología para que nos hablen de sus descubrimientos, no solo en México, sino en otras áreas como Guatemala, Perú y España. Hemos elaborado un programa muy interesante que irá desde las cabezas monumentales olmecas hasta los vasos funerarios hallados en las pirámides de las selvas mayas. También abordaremos la última tecnología que se aplica en la ciencia arqueológica. Entre otras técnicas, se platicará acerca del LiDAR, de los drones y cómo estas técnicas contribuyen a un mejor conocimiento de las civilizaciones antiguas. Las conferencias tendrán lugar en el aula mayor del Colegio Nacional, aquí en la calle Donceles, en el Centro Histórico de la Ciudad de México, y la entrada es libre. Los esperamos a todos. Muchas gracias.
cualquier pretexto es bueno para visitar el centro histórico de la Ciudad de México. Hay edificios maravillosos, rincones que usted jamás ha visto y desde luego hay sitios que son de visita obligada. Me refiero al Colegio Nacional. Un espacio donde se junta la inteligencia, la imaginación, el arte, la ciencia y algo muy bonito, la conversación y la amistad. En este edificio hay ahora un nuevo espacio. Es luminoso, es grato, es agradable y está el mejor amigo de usted, mío y de todos nosotros. ¿Sabe qué es? Un libro, muchos libros, una historia, muchas vidas que van a enriquecer la nuestra. Vengan a visitar la librería del Colegio Nacional.
Sí, me parece lindo.
Have been destroyed by Spartacus.
Spartacus, a motion picture unequaled in the entire history of filmmaking, unlikely ever to be surpassed. In the tenderness.
Have been destroyed by Spartacus.
Spartacus, a motion picture.
El verde ya no tiene pilas. Ok, el otro no sé. Sí.
El verde está muriendo.
So it is a great pleasure for me to introduce Roger. He's from Universidad Autónoma de Sinaloa, and he's going to talk to us about quantum field theories in 4 dimensions with a particular method. So thank you, Roger.
Thank you. Thank you, everybody, for being here. Thank you for the invitation to this place. I've never been here in this site. This is my first time here giving a talk. So what I'm going to present is going to be a new method that we are implementing for computations of observables in 4 dimensions. So the method is based in this in a formalism, and we are trying to test all in different processes. Okay. So as an introduction, I don't need, well, thanks to be after these 2 great lecturers, I don't need to convince yourself that we need a lot of computation with more loops and more legs, more in the sense of in order to give more predictions, to be more accurate predictions, we need to go into further loops. But the thing is that if we want to compare with the observables, observables are finite. They don't present these singularities that the speakers they were saying. But this is the actual method that we are that we can use. We are using nowadays. So, but we know that the description of the fundamental interactions relies on quantum field theories. That is why we are here. And as Professor Lance Dixon was saying, so scattering amplitudes have singularities. So disentangle the ultraviolet and the infrared singularities is a major task in this field. And they represent, from the theoretical point of view, the phenomenology they needed in order to have these quantum fluctuations of the total cross-section. So the accurate prediction for the LHC and the future circular collider that it may be going to be approved, or in other future experiments, they are going to need these amplitudes to be computed at the highest accuracy possible from theory, because from experimentalists they are going to have another issues from the constructions and from the installing the machines and everything. Okay, so then this is the plot that Professor Dixon was showing, just to explain to us and to convince ourselves that if you want to give a precise measurement, it is not only the leading order piece that is going to be needed, but you need also the next to leading order and the next to leading order. And in order to be into the safe place in which the series is going to converge, in this particular plot, you will see that you need to go to the end to the 3 leading order piece, which is this red band. So we expect that if you go further into the n to the 4, so you're going to be inside the red band. So we are in the convergence of the series, right? In the area where the series is going to be convergent. And so then all of these calculations, they are full in the sense that they compute the full cross-section, they integrate over all the phase space. But if you want to compare with the actual predictions at the LHC of other colliders, you need to do in a Monte Carlo simulations. And in the Monte Carlo simulation, you cannot put freely your epsilon poles or your parameters. Is hard. So to know what is the behavior of the amplitude of the cross-section, you would need to have the integrand. And the integrand is what we are going to show that has these divergences. So there are theoretical issues that we know now. If you want to go into more and more accurate prediction, so the integrands are going to be usually very lengthy. So it's going to be a lot of terms. The number of Feynman diagram that Professor and Malena was showing is increasing a lot. So the 500,000 or a 250,000 from this particular processes. Imagine that if you want to go into more and more theoretical accurate calculations, so you're going to need more and more loops and legs. And so then afterwards, once you compute all the Feynman diagrams, you implement that into the Monte Carlo simulation in order to give the theoretical prediction. But no Monte Carlo, usually they compute, not all of them, but usually they compute first at the first step. They compute the poles and they show that the cancellation of each pole is going to be achieved at locally. The cancellation is local, so the computation of the contra terms is going to be very, very complicated to achieve, because this has to be, you give one particular point into the phase space and you're going to have an infinite. So this infinite you have to cancel point by point in the phase space. So it is complicated to find a universal counterterm for all of them. And so as Malena was saying, and also from the audience, they were asking about new physics searches. So they're always going to be hidden in all these Feynman diagrammatic approach. So one of these diagrams is going to be responsible of one of these bumps. So extract the information of this only and single Feynman diagram is complicated. To disentangle all of this background around your signal. So then we need to go and we need to find new methods to compute this theoretical prediction, because if you imagine that on the future years the FCC is going to ask you for more predictions, they're going to ask you so for n to the 3 or n to the 4 as a basics. So afterwards there's going to be more and more loops or more and more legs. So now the next to leading order calculation is barely, we say that it's solvable. We can compute in a click. You can download on your computer and you can compute it. But if you go to the next to leading order piece, next to leading order piece is going to be harder. You have to ask to the phenomenologists to give you the Monte Carlo for this particular process. And if you go to n to the cube for a particular process, there's also not an implemented machine to do that. So you have to deal with that. Because all of the poles that the speaker were saying, in every process, the poles are going to move around your phase space. So you don't know where is the pole from your next particular process. So what are the, if we want to go to the 4 dimensions, so I'm going to talk about this formalism, the 4-dimensional unsubtraction, which is called for short FDU, and it's an attempt to formulate the quantum field theories in 4 dimensions. It is based on a series of papers, and in the first paper by Stefano Catani and collaborators, they were saying that, so the first steps of the loop tree duality. The loop tree duality, what it says that, I'm going to say after, next slide, but what it says is that the loop momenta, you can map into the phase space momenta. So the integrals is going to be related, and so then after the computation of the loop integral, you can map one of these integrals into one of the real integrals. And so the cancellation is at the integrand level and not at the integral level. But we need to review a little bit of this formalism. Then the application of the loop tree duality here is going to be the first attempt to match this cancellation of singularities at the integrand level. So then the cross-section is finite. So then you can take the limit to epsilon to infinity at the integrand level, epsilon to 0 at the integrand level. So the remaining pieces that your Monte Carlo is going to compute is finite. So you don't need to pass through all this epsilon disentanglement. So here, this is a series of papers of the FDU. So on the first one, they treat the massless case. On the next one, there's going to be the massive case. Then there's going to be another series of papers when they try to implement in a more numerical approach. So the singular structure, it's always the problem of the singularities and the thresholds and all of these particular singularities in the phase space. So in this paper, they try to analyze, they try, and they did, the analysis of the singular structure of the poles, and then the first numerical approach of the 2-loop is given in this one, and 2 weeks ago, we just show that for the multi-loop calculation, you can try to attempt so the first steps to go into this loop tree duality to the singular structure of the poles. So we show that the cancellation is coming. Not the full calculation, but we hope that it's going to be treated in the next papers. So what is the loop tree duality? We know that whatever one loop integrals is decomposed with. This is a scalar case, massive scalar case. You have the integral of this loop momenta. So what you do is that it's the product of this kind of denominators, the Feynman propagators. the I0 prescription established the particles are going to flow in the forward direction in time. So this is the basic idea. So we know, so from quantum field theory, that what we have, the problems are in the denominators. In the numerators, basically, they can be whatever they want, but the denominators is where the singularities appear. So after applying the Cauchy residues theorem in a very fancy way, so they can show that this loop integral, they can be decomposed as a sum of this delta tilde, where this delta tilde sets the parameter, the momenta qi on shell. So if the momenta qi is on shell, that means that it's real in the sense of the real radiation. So it turns out that this put it on shell, one of the internal lines, they can be, so it was the first thought that they can be mapped. There should be a mapping in between the variables, the unique variable, the unique mapping. So then you can cancel the integrals at the integrand level. So the price that you have to take is that you have to they have to put these dual propagators, where this GD is defined exactly the same, more or less, to the Feynman propagator, but you have to change the prescription. At one loop, there's not a problem, because this difference in the momenta, defined as the internal lines, is always cancel the loop momenta. So the integrals, it doesn't matter. So you just only take the external momenta, so the integral, it doesn't matter. So what is going to be a problem? It's going to be a problem when you go up to 2 loops or 3 loops, because you can have, for instance, here the momenta of L1 and here the momenta of L2. And you have to integrate over L1 and L2. So the problem is that there is going to be a threshold when you pass from one to another. So this is one of the key points as the higher loops. But at one loop, this is not a real problem, because this is just only going to be a plus or a minus I0 prescription. So Lorentz invariance is recovered only when you sum over all the internal lines, or all the cuts. The good things about this is that there was previously a paper by Feynman, the Feynman tree theorem, and in this Feynman tree theorem they cut all of the internal lines, but here just only cut one line. So so all the amplitudes that you have of all the integrand that you have, there is like a real one-to-one connection to the real radiation. So this is the important thing. So in the derivation of this formula, you have to just only define this eta mu 4 vector, like a future-like 4 vector, and for simplicity we take 1 and 0. It's still valid. So one of the first papers that they showed us, if they compare in this paper the numerical implementation by loop tools and SecDec versus the loop tree duality, so the accuracy is okay, but the time consuming to these integrals is very fast. And this is one of the advantages of the loop tree duality. So this is a pentagon, a tensor pentagon of rank 2, 3, 4, 3, 2 and 3. They have also this plot for hexagons, and the convergence of this computationally is very fast. It's extremely fast in the loop tree duality. So imagine that you are going to do a Monte Carlo. In a Monte Carlo, you don't have just only one point. This P16, P17, and P18, 19 is one point in the phase space. So then you have to think about in the Monte Carlo. In the Monte Carlo, you run through 1,000 of a million of events. And so then if you want to run this, it's better if you have a powerful machine. In my machine, I cannot do it. But that's why they have this technology in the LHC and in the colliders. So this was the first attempt. So then we just only say, okay, we think because it's just only the Cauchy residues theory. So we say, okay, we know that it was going to work. So what are we going to do with this approach? So we go into the quantum field theory in 4 dimensions. So this was the first case that we studied. So we know that this massless scalar case when you have the singularities. So we know that the cross-section level. So this correction is going to be finite. All of the corrections are finite. If you add at the cross-section level, not at the amplitude level. All of them are finite. So the loop tree duality says, okay, if you have this triangle diagram, and you map, and you need to add with a real correction, with a real radiation. So we say, okay, but here one of the lines is on shell. So this is and you have all the combinations, right? So what was the thought that we had at that moment? So if you apply the loop tree duality, you can match the virtual corrections with the real contribution at the integrand level, and then if they don't have divergences at the integrand level, you take the limit to epsilon to 0, and it's going to be finite. And that was the first case. So the infrared divergences are going to, well, if you diagrammatically, if you apply the loop tree duality to the triangle, you have that one cut here, and one cut there. And so then you separate all of the singularities into 3 integrals. But the problem here that you have to take care is that, for instance, when Professor Lance said that the bubble diagram is 0, of course it's 0, but you have 1 over epsilon UV minus 1 over epsilon IR, the infrared, so you cannot drop all of these things again. You cannot drop all of them. You have to take care of all of the singularities, because every time that you implement one of the cuts, so the singularities are going to be one of these. Q1 could have, for instance, takes the infrared part of the bubble, and another cut could take the UV part of the bubble. So you cannot cancel. You cannot say 1 over epsilon UV is exactly the same as the 1 over epsilon infrared. So that's why it's more a little bit more complicated on the construction of this FDU. However, you can define, for instance, the real radiation of an I particle. This is the phase space of 1 to 3, which is the process that we were analyzing at the scalar case. So the virtual, we say that this is the sum over this I matrix element, and this I is going to be one of the integrals that you have. So all these the variables here and the variables there should be related, and that they are related by momentum conservation. P1 and P2 is equal to P1 prime, P2 prime, and the P radiated prime. So they have to be a connection between them. So what they do is that we claim that if you add this piece I virtual plus this I real, it allows us to have a 4-dimensional representation of the integrand. And so then the computation has to be finite. Of course, the mapping is 1 by 1. So if you cut one of the Q1, you have always Q1 on shell. So then the mapping has to be like one of these in the real corrections, being the mapping exactly like this. So this is the mapping. The mapping is that the real radiation is equal to Q1, and the P1 prime is this mapping, and this P2 prime is this alpha 1. And in alpha, they are hidden the collinear and soft singularities. However, if you add all of them, you have the relation of momentum conservation. Of course, you have your alpha 1 that you put here, and this related with this. If you square it, you will find a relationship between all of the momentum that you have in your integrand. But what is important is that when you compute these three sigma 1s, this is order epsilon, so this is a 0. So this is they don't have a poles and they don't have a poles. So it means that if you take the integrand that you computed here, you can take the limit to 0, the epsilon to 0, and the total cross-section is going to be finite. And this is the result that you have from standard conventional dimensional regularization. So the issue here is that if you have ultraviolet, if you have ultraviolet, then you have the propagators, and if you can construct the counterterm, and the counterterm is like this, you just only have to square the bubble, for instance, the bubble diagram, and then the loop tree dualization of this, which is the Cauchy residues theorem at multiple poles. And so you just only apply it, and you have this expression. So at the end, you can see that if you take the bubble, which is this diagram, and you subtract the UV counterterm in the loop tree duality formalism, so you have this expression, and this expression is finite at the epsilon You can plug in your computer, and it's going to be this expression here. So there's another important fact that this mu uv is equal to q over 2, in order that there is no intersection in the hyperboloids when you put into this into the integrand. And this is a physical interpretation of that. This is the renormalization and factorization scale. This is not exactly that, but we usually do these bands by varying these scales around q over 2 and 2q. And this is one of the, one we can say that within this formalism you can say why you need to be q over 2 and not another value. So we go to QCD in 4 dimensions. So the first basic example is that you have in the textbook the gamma to QQ bar at next to the in order. These are the pieces. And if you compute the real correction, then you compute the ultraviolet, you do the mappings, and you do all of the steps that I showed, you find these 3 results for the sigma 1 tilde, sigma 2 tilde, and sigma v bar. And all of them are free of epsilons. So if you do, we have a 4-dimensional representation of these integrals. If you want to see, I can show you, but it is big. Anyways, the thing is that the most important thing is that we can compute it in 4 dimensions, avoiding all of the terms of the singularities at the integrand level. So, but what is the most important? We need to go to the next to leading order piece. The group has computed the Higgs to gamma gamma at next to leading order. The amplitude at next to leading order is a 2-loop amplitude. I do not show you the results analytically because we cannot compare here, but because it also does not say anything about physics. The physics is hidden in this plot. You can go into the papers and you can see the exact matching, and the expression that you find in the paper are in 4 dimensions. Because of the amplitude, this amplitude in particular has only UV singularities, so then they implement the procedure of the IFDU, and they find exactly the cancellation of the poles at the integrand level. So they show a perfect matching. So what are we going to do now? So we want to do multi-loop calculations. So with regard to the multi-loop case, there are recent results we selected by topology. This is the first, we call it maximal loop topology, which is the sunrise and adding more. We have this next to maximal loop topology, which is appears at 3 loops, and this is also the Mercedes-Benz, which is the first one that appears at 3 loops. But we can add more and more internal legs. So we analyze this within multiple powers of the denominators. We also apply this algorithm for whatever numerator, and what we found is that you can reduce this amplitude into this formula that is diagrammatically says that you put all these lines on shell, you put all these lines on shell, and the I is the only one which remains off shell. But what is the big advantage is that this is simple and is very symmetric, and moreover, if you analyze the next to maximal loop topology, what you find is a very compact expressions, which is written in this kind of with this mathematical thing. But the thing is that you can build, as Professor said, that you want to recycle your information. You don't want to do it one over and over again. So if I want to compute the next to maximal loop topology, which is this diagram, to n loops, n minus 1 loops. So then you need only to know what is the maximal loop topology of this, the maximal loop topology, maximal loop topology. All of these algorithm we have been showing that it is exactly the same as computing this, but this is faster. And we did also the next to maximal loop topology, and so it's also the same. So we can recycle the information of this next to maximal and the maximal loop topology in order to build your next to maximal loop topology. So we just only apply the Cauchy residues theorem, which is the loop duality, in order to build this representation of these integrals. Now, what we are wanting to do is like combine this algorithm with a real processes, which is an ongoing project. So the conclusion is that we, and in this audience, I think that we are here because quantum field theory is one of the basic mathematical tools that we have for compute observables in QCD or in electroweak. We know that you have to compute quantum corrections, and within these quantum corrections they're going to appear epsilon poles. And in these epsilon poles, you have to deal with the cancellation of them before or after the integration. And here what we have, I wanted to convince you is that, and this is, I didn't say explicitly, but within this algorithm, so the cancellation is local, and it allows us to do the representation in four space-time dimensions. So I think that is everything that I wanted to say.
Thank you, Roger. We have time for maybe one question. Yes? Yes?
I guess there was also last year there were some papers by Stefan Weinzierl and also the Zurich group. I think it's a little tricky to get these prescriptions right too. How does your work compare with their work maybe?
So let's say that they were doing the loop tree duality also, the same formalism. But the thing is that they were computing the amplitudes above the threshold. So then they don't have, so they can do it numerically. But for us, if you want to do the full computation, you have to consider also the thresholds. And in this final result that I showed, all these thresholds cancelled. The threshold is going to be cancelled because the physical observables are only in the infrared and the UV. But this is they say that the settings is the same, but they are considering one in which the singularities, the threshold singularities doesn't take place.
Right. So we'll be around for more discussions during the break. So let's thank Roger again.
Thank you.
And we will continue with our next speaker. Right, so, nice. So our next speaker is Alberto Guijosa. He is from Instituto de Ciencias Nucleares at the National University here in Mexico. And he's going to talk to us about entanglement, QFT, and gravity.
Thanks.
Thank you.
Thanks to Lorenzo and Felipe for the invitation. Thank you all for being here. And we've had 3 very nice talks on amplitudes now in a row. And now I apologize because I'm going to switch topics. My motivation for this talk is work that I've done with various people, but I will choose not to actually tell you in any detail about our results, because I prefer to give you a brief overview of the general ideas, just for the simple reason that that's a better investment of your time. Okay, so we all know that quantum entanglement, of course, has long been known to be a useful resource for quantum information. But the main message that I want to get across today is that in recent decades it's also been found to be a very useful concept. Entanglement is a very useful concept directly in quantum field theory and also, as it turns out, in quantum gravity. So just for starters, as we all know, entanglement refers to states, entangled states refer to states that cannot be factorized into subsystems. So the typical example is for example, talking about 2 spin 1/2 particles. So this is an example of a not entangled state because its spin is undecided on its own, and you can assign it a definite state. Whereas this, which is not factorizable, is an example, of course, of an entangled state in which the indecision of these subsystems is shared among them, and there's no definite state for each system separately, for each subsystem separately. Now, how can we quantify this notion? Given any quantum system whatsoever, if we need to do first two things. One is to split our system into two subsystems. So we choose a particular bipartitioning of our system. So I'm illustrating that here in a lattice of atoms. I'm dividing it into these atoms in red that I'm calling the set A, and then the complement that I'm illustrating in green. And then beyond this division of the degrees of freedom, we also choose a specific state for our overall system. So I'm going to express that generally as a density matrix here, the rho total. Then with those two ingredients, we can do the following two steps. First of all, we can take the trace over the degrees of freedom in the complement, so over the green atoms in this illustration. And the intuitive idea there, the useful way to say this intuitively is that we're summing over all possible states of those degrees of freedom that are not accessible to us, say in an experimental sense. After doing that, we obtain what's known as the reduced density matrix for a subsystem A, and this expresses the best available knowledge we have for that part of the system. Now, having that description of the red atoms in this case, or generically or subsystem A, the next step is we can just compute the von Neumann entropy of that density matrix. So that measures how non-pure that density matrix is. And if we do that in the simple example that I mentioned before, in the case of two spins, then we can easily see that if we have a state like this that can be factorized, and we do this computation, then this von Neumann entropy, or known in this setting as the entanglement entropy, turns out to be 0, so expressing the fact that this is not an entangled state. But if we switch the signs there so that this is no longer a factorizable state, then we do the computation, and for this particular state, we get this result, so expressing the fact that indeed this is an entangled state. So in short, what one learns is that this quantity here, known as the entanglement entropy, quantifies entanglement between the two subsystems that we chose in the given state. So the larger this quantity, the more entanglement there is between these sets of degrees of freedom. Now it's called entropy on the one hand because it's a generalization of the usual thermal entropy. So we can easily see that if one plugs into here a thermal density matrix, then this reduces to the usual notion of thermal entropy. More generally, it's entropy in this modern sense of information. So that's what it's expressing. Okay, now this quantity entanglement entropy has been proven rigorously to satisfy a number of properties, a large list of properties for any quantum system, so that's quite impressive. Of course, the quantum systems of interest to us are field theory, so now let me talk about that. What I want to transmit to you here is that in the past couple of decades, it has become clear that it is in fact very useful, as I said before, to analyze quantum field theories from this perspective of computing entanglement entropy. So just as I said before, if we're going to look at this particular quantum system, any quantum field theory, we need the two ingredients that I mentioned before. So first, we need to choose a state over quantum fields. So say the easiest thing is just to choose the vacuum. Now, when one first hears about exploring or looking for entanglement in the vacuum, one might be confused because it's easy to picture, of course, entanglement between two spins, two particles. But of course, from the field theory perspective, we're very familiar with the fact that the vacuum is not equivalent to saying that there's nothing there. In the vacuum, one still has the fields and they're in the ground state, so they're doing something, and it's therefore a valid question to ask how much entanglement there is in that particular state. Okay, so then we have a particular state. The other ingredient that we need, as I mentioned before, is to choose a bipartitioning, so a separation into two sets of degrees of freedom. In a quantum field theory, of course, degrees of freedom are organized spatially, so a very natural way to bipartition is just to choose a surface. You choose an imaginary surface that separates degrees of freedom that I'm going to call A in some region with its complement. And then we ask, how entangled in this particular state of the quantum fields, how entangled are the fields here with the fields in the rest of the universe? And with that, we compute with this quantity that I described before, the entanglement entropy. Now, for sure, this is different from the usual perspective that we take when we take any course on field theory. In the usual approach, what we compute are correlators, and we usually don't emphasize enough to students in particular the fact that these correlations arise precisely from the fact that in the given states, typically the vacuum, the fields at these locations are in fact entangled. So we've always been studying entanglement, It's just that we usually don't emphasize that point. And in fact, correlators that we usually deal with are bounded, can be shown to be bounded by entanglement. So in short, what I'm trying to, the takeaway message from this portion of the talk is that whereas in the standard story that we all learn to compute correlators in field theory, what we're doing there is using local operators as probes to examine the entanglement pattern of a state, or say the vacuum. That's what we're doing. And using different probes, that is to say, using different operators for the same state, we can obtain different answers, of course. But now from this newer perspective, if we use entanglement entropy, we compute entanglement entropy for our state, then we're getting direct access to the underlying entanglement pattern in our field theory state. So in that sense, this perspective is more fundamental. We're getting at this underlying entanglement. Okay, now this perspective has led to insight along various fronts. In particular, most importantly, it has been found that entanglement entropy encodes interesting information about the renormalization group in field theory. So mainly, it leads to proofs of C theorems and identification of C functions. So for those of you who don't know what that is, it's just statements of certain quantities that are monotonically decreasing under renormalization group flow. That is to say, when you examine your field theory at larger and larger distance scales, lower and lower energy scales. Okay, so that's one type of examples, and there are also other types of constraints on renormalization group flows. In a second direction, entanglement entropy also serves as a tool to diagnose phase transitions in field theories, so that's also an important development. And for these reasons, you already get a glimpse of the fact that it's actually interesting to try to compute this quantity, entanglement entropy, in field theory. But as it turns out, it is actually very difficult to compute, even in free field theories. There's a song and dance that one needs to go through, goes by the name of replica trick. And only a very limited number of cases are accessible through traditional field theoretic tools. And because of that, then we search for new tools. And now I'm going to tell you about, or remind you about, a tool that we had now for 20 years, which is known as the ADS-CFT correspondence. And the more general form of this statement is that you can have a quantum field theory in a certain number of space-time dimensions, for example, 3+1, which would be a familiar one. On the other hand, you can have a quantum gravity theory on a space-time that is, of course, dynamical because it's gravity, with a larger number of dimensions, at least one more. And the ADS-CFT correspondence is just the remarkable statement that these two can be the same. So what one is saying is that despite appearances, these two drastically different, or apparently very drastically different theories are in fact just alternative languages to describe exactly the same physics. There's just one physical system that we're talking about, and we can describe it from two very different perspectives. And there is in fact a dictionary that faithfully translates from one language to the other and back. Okay, so that's the generic statement about ADS-CFT. Now, initially one just had a very limited number of examples of this correspondence, but over the years, more and more examples have come to be understood in quite large detail. And as far as we know, this type of translation could conceivably apply for all quantum field theories, but to date, we only know it in full control, in full quantitative control, only for certain classes of quantum field theories. So that's the status. For example, an interesting, known and understood case or classes of examples of this is when the quantum field theory on this side happens to be a non-abelian Gates theory, which is of course a case of huge interest to us. In that case, certainly the quantum gravity theory on this side is a string theory. So that's a particular subset of statements that one is making here. Okay, now in this setting, let me put it into a cartoon now. The field theory lives in, well, there's time, which I'm not including in the picture, and then there's some number of spatial dimensions, which I'm labeling as X here, this horizontal dimensions in my picture. What I'm saying is that the gravitational theory lives in at least one more dimension, so there are these same dimensions here, X, horizontally, but there's this extra dimension that I'm indicating vertically, that's known for historical reasons as a radial direction. And then the natural question is, what the hell is this in the original language, if there's really a dictionary that faithfully translates between the two? Well, as it turns out, this extra coordinate, what it means on this side is just the energy scale of your field theory. So when one is describing a field theory, one first of all decides which point on space-time to sit to carry out an experiment. But then a second decision is what your resolution scale, be it a distance scale or an energy scale of your experiment is going to be. So you decide to sit, say, at the LHC, and you decide to do experiments with a certain energy scale. Well, that energy scale, this mu here, which is also the energy scale of the renormalization group, is precisely what maps to this extra dimension here. In such a way then that going very, very high up in my drawing corresponds to going to the ultraviolet of the quantum field theory, so what happens at high energies, and going very low in my drawing corresponds to the infrared of the field theory on the left-hand side. So then, what I'm saying in summary is that at heart, this equivalence, the ADS-CFT correspondence, is known in retrospect to be a geometrization of the renormalization group. So this is information about how this field theory has a different aspect, how it changes, how it evolves as one changes the energy scale, the resolution scale, is geometrized in this sense. It's deposited at different vertical positions in the drawing on the right. Okay, now in particular, this leads to the following consequence. One normally likes to talk about quantum field theories that are well-defined at arbitrarily high energies, and such theories will necessarily reduce to conformal field theories in the ultraviolet, so theories that are scale invariant in particular. Well, that refers to something happening all the way here in the ultraviolet, and what that is the geometry here, as it turns out, because of the symmetries here, has to reduce to what's known by the relativists as anti-de Sitter spacetime. So the simplest spacetime after Minkowski, it's just a spacetime with a constant negative curvature. That's what you get. And that's what I was referring to, or that's an example of what I was referring to as with the statement here about boundary conditions. So the geometry inside can, of course, be drastically deformed because this is a gravitational theory, but at the top of my drawings, the geometry has to reduce to ADS in this class of examples. So that explains the name. Okay, now, again, going back to the generic idea, one has a field theory, and on the other side, one has a quantum gravity theory. Now, of course, quantum gravity is an intimidating beast, and if one wants to start talking about it, it's natural to do the easiest thing first. So one looks at easy calculations in the regime where gravity is classical and the geometry is weakly curved. And if one uses the dictionary to go to the other side, that turns out to correspond to having many fields in this quantum field theory here, and also those fields are strongly coupled. Now, interestingly, that's of course precisely the regime of the quantum field theory that we certainly do not understand with traditional tools. So what I'm saying is that easy computations on this side can give us access to this previously inaccessible region. And indeed, on the gravity side, there's a simple recipe to compute quantum field theory correlators, to regularize them, renormalize them, and so on. So that in that sense, this statement has certainly been very useful. Now, going back to our original intention, let me ask then how to compute entanglement entropy, which I told you is an interesting object to compute. In the field theory, how to use this tool, which is ADS-CFT, to do it on the gravity side. Well, the recipe ends up being the following. First, you draw this same boundary here that you had between A and its complement, the boundary of A, you draw at the top of my drawing on the right-hand side, on the gravity description. Why at the top? Because that's ultraviolet information. The location of this imaginary surface is ultraviolet information. Okay, then the next step is you hang from there a surface, and you look at all surfaces that can be hung from there, surfaces with a restriction that they can be deformed continuously back up to the boundary. And then you compute the area of such surfaces, and you choose the surface, the special surface that minimizes the area, that has a minimal area for those boundary conditions. You divide that area by four times the Newton constant. There's a Newton constant here because there's gravity. And these folks here, Ryu and Takayanagi in 2006, proposed that this is actually, surprisingly, the way to compute what we want to compute on this side, which is the entanglement entropy. Now, just a disclaimer here, this formula is actually a simplified version of the formula, which is valid in the regime that I described before. When the quantum field theory on this side has many fields, in fact infinitely many fields, and it also has infinitely strong coupling. But extensions away from that point are known. So I'm not going to go into them, but that's what we're talking about. Okay, now we look at this formula, and as I mentioned before, this entanglement entropy on the left-hand side is a generalization of the usual thermal entropy. Now what we're seeing in this magical formula on the right-hand side, many of you have already recognized as a generalization of the usual Bekenstein-Hawking formula for the entropy of black holes. So this is a very surprising connection. In particular, this is a highly quantum object, and this is just a classical area. And yet, this seemingly crazy formula has been found to lead to results that are consistent with all expected properties for entanglement entropy, and in fact has found a derivation in the work of Lekowitz and Maldacena many years later, about 7 years later than the original proposal by Ryo and Takayanagi. Okay, now, so then the bottom line there of this part is that I'm saying if we start with this formula and we go from the easy side to the difficult side, we're learning that ADS-CFT is a very efficient tool to compute this particular quantity, among others, which is entanglement. Okay? Now let me just briefly mention that in this context, work that we've done has related to how to renormalize entanglement entropy, renormalize it coming from the gravity side, but I won't say any more about that for lack of time. Now, this direction here is already, of course, hugely important, hugely useful in the practical sense. But from a conceptual sense, it's even more interesting to go in the other direction. Because, see, what's happening in this direction is nothing short of a miracle. What I'm saying is that one starts with field theory, non-gravitational field theory, in few dimensions. And then out of that, these degrees of freedom somehow secretly know, somehow they know a way to reassemble themselves into degrees of freedom that describe a larger geometry and moreover a dynamical geometry. Now in more detail, the formula that I just described, the Ryu-Takayanagi formula, tells us that if we know the pattern of entanglement in our quantum field theory state, say the vacuum, then through that formula we can compute these areas of minimal area surfaces on the gravity side. And therefore, from that information, we can deduce what the geometry is, how the spacetime is curved on this state, which is the translation of this particular quantum field theoretic state, say the vacuum. Okay? So in short, what I'm saying is, one wonders where the information about this curved geometry is on this side. Well, Ryo and Takayanagi are telling us that the answer is it's hidden in the pattern of entanglement, of quantum entanglement in this field theory state. Okay, now again, just very briefly mentioning, we've done work in this context, going in this direction, for the particular case when one only has access to a finite portion of the quantum field theory. But again, I won't go into detail to that, because I want to use the remaining time to talk about, just very briefly, 3 useful lessons that have been understood with this technology. One is, well, I told you before that each particular quantum field theory state here can be translated into a particular curved geometry on this side. So in short, you can read off the metric on this side by figuring out how much entanglement you have on this side. Now, suppose you start with a vacuum, and then the vacuum of the field theory, and then you add on top of that some small excitations. Well, certainly what will happen is that the entanglement entropy, the pattern of entanglement will change in some particular way, no? And there's a formula for that you can deduce from just the definition of entanglement entropy. So there's a certain statement there. Okay, now if we translate to the other side, what will this tell us? Well, based on what I said before, this will imply on the gravity side that small excitations, so when you pass to a different state that is no longer the one, the translation of the vacuum, but this translation of these small excitations on top, well, since the pattern of entanglement changes, then the space-time geometry will change on this side, okay? So that sounds good. I mean, we're trying to construct here a gravity theory or reproduce a gravity theory. It sounds appropriate that if you have excitations, they will distort the geometry, no? So the geometry is dynamical. Okay, but now if you look at this in more detail, if you translate this formula, this particular way in which entanglement changes to this side, surprisingly, what you find out is precisely the Einstein equation. So what I'm saying is that, hard to believe as it is, one can start purely with the language of quantum entanglement in the field theory and translate that into this other language using ADS-CFT, and one deduces the Einstein equation just from the story of entanglement. So that's a very remarkable achievement. Okay. Now, one other topic that I want to talk about is that in this context, the overall lesson that has been extracted is that the role played by entanglement in the gravity side is that entanglement is sort of the glue that holds geometry together. And there are many examples of that, but let me give you the first one that we had and the simpler one. So suppose now on the field theory side, I take 2 field theories, or let's say 2 copies of the same field theory, and I take them to be in certain state, but importantly, they're decoupled from one another, so they're not interacting. They're strongly interacting in themselves, but they're not interacting with one another. And I choose them to be first in an unentangled state. Okay, so a factorizable state. This field theory is doing what it wants to do, and this other field theory is doing its separate thing. Okay, now as you might expect, that corresponds to, in this ADS-CFT translation, that this field theory state has its corresponding geometry, and this as well, but those are two disconnected geometries, as it's natural to expect. Okay, now the novelty is that if you add entanglement to this picture, so now you have, still the theories are not interacting, but now you pick a state that is entangled, in fact, very entangled in a particular sense among these field theories. Well, now you find out that the geometry here is suddenly connected. Now the two geometries that were disconnected before are suddenly connected, and there's a bridge going from one side to the other. There's this, what relatives call a wormhole, going from one side to the other. So in that sense, that's just a very specific example of how entanglement plays the role of the glue that connects pieces of geometry together, that assembles geometries together. Now, of course, you know that I had to mention this example in particular to make contact with the conference poster, which conveniently included a wormhole. Okay, and then the final item I want to talk about, the final example of an important insight that's been understood. Well, actually, let me just briefly say that once one has this setting with a lot of entanglement, one can do useful things with it. In particular, one can talk about quantum teleportation, which is well known in quantum information theory. As it turns out, if one does that in this setting, one ends up learning that, well, for teleportation, one needs to add an interaction, in fact, now between the two pieces. If one does the corresponding thing on the gravity side, one finds that now, all of a sudden, you can send information through that bridge. So the wormhole becomes traversable, whereas it wasn't before. So teleportation corresponds to just flowing through this bridge, through this wormhole, as it turns out. That's what's done by these people. Okay, and then I cannot end before mentioning this very important and very recent development, that using this same set of tools, this Ryuta-Kayanagi formula and generalizations and other insights associated with this story in ADS-CFT, there are papers from just October and November where very important progress has been made on the black hole information paradox. As most of you know, this paradox refers to the idea that, well, Hawking discovered that black holes are not black. They slowly radiate until eventually they would evaporate. And then he originally postulated that that would mean that all information about how the black hole was assembled will be lost. No? And since then, there's been this challenge of finding out whether or not that's true, whether in fact in the Hawking radiation there is information about the inside of the black hole and what went into the black hole. Well, there's no time, of course, to review this in any detail, but let me just show you a picture here and tell you that with these tools, we found in specific settings available through this ADS-CFT correspondence, in some idealized settings, that in fact, that indeed, as expected, the radiation does eventually contain the information about the inside of the black hole. Okay, so let me not stop there because we don't have time. Let me just summarize then. One of the main things I told you is, well, this is a conference about new trends in quantum field theory. The new trend that I've been trying to summarize here for you is looking at quantum field theory through the lens of entanglement. And I've tried to argue very quickly that that's turned out to be very, very useful. So it will continue to be useful in the coming years. Now, I've also reminded you that there's this tool available now for 20 years, the ADS-CFT correspondence, which establishes a very surprising equivalence between non-gravitational quantum field theories and theories of quantum gravity. It's certainly a useful tool to compute entanglement, and it's shown us lots of, well, given us lots of insight in that direction, but also other properties in certain strongly coupled quantum field theories. I also explained that at least in certain model universes, when one can discuss, one can do computations in these gravitational theories under some reasonable control, entanglement is found to play a crucial role in the emergence of space-time and gravity. It sort of stitches geometry together. And let me just finish by mentioning that other quantum information theory concepts have also been found to be relevant. tensor networks, quantum error correction, relative entropy, complexity, chaos, entanglement and purification, negativity, and the list keeps growing by the day. So there are many useful concepts that people in this community have explored for many years, and now we've imported them into the setting of quantum field theory and gravity, and they have a very interesting interplay through holography, or this holographic or ADS-CFT correspondence. Okay, so I'll shut up now, and thank you very much for your attention.
Thank you, Alberto. We have time for one question. Yes?
So you have discussed that from entanglement information you can recover Einstein equations, then with and without cosmological constant, either sign, and what about magnitude?
No, thanks for the question, for clarification. Secretly, in my energy momentum tensor that I wrote there, I don't know if I go back to that, but in my energy momentum tensor, yes, here, I was including the cosmological constant in the energy momentum tensor. So in the examples that we have under most control, in ADS-CFT with this tool, what happens is on the gravity side, you have this asymptotic anti-de Sitter boundary conditions. So the cosmological constant is negative, certainly different from our universe. And therefore you reproduce Einstein's equation, but with a negative cosmological constant. Okay, so that's the particular setting. So thanks for the question. Yes.
And you showed variations on the shape of the surface on the right-hand side, and also variations on whether you're on your lowest level or excited state. In this left-hand side. How about variations, or how dependent is the right-hand side on the choosing of A and AC? So you define this system that you have access to, but that's a external decision. What happens in the right-hand
it's also interesting to explore that. It's also very interesting to explore that. In fact, well, let me just flip quickly to my backup slides.
Because that's equivalent of making a decision on the size of the system and the number of degrees of freedom.
Tracking the dependence, well, actually the previous one. Tracking the dependence on the size and also the shape of the entanglement region is actually also very interesting. The simplest idea is just to choose a sphere with a particular radius and see how the result changes with the radius. It turns out that when one looks at that, well, to begin with, you have a divergent. This is a divergent quantity, but buried within that, there's a quantity that is independent of your regularization, and that quantity is precisely the one that's been found to be make contact with the renormalization group. So the coefficient makes contact with this so-called A theorem that was only proved recently, well, not many years ago by Komargotsky and Schwimmer. And from this technology in ADS-CFT, it was found that, well, this statement here only applies for even space-time dimension, and nothing was known for odd space-time dimension. With this technology, an extension, a generalization of this was found to odd space-time dimension, known as the F theorem. But that, again, it depends very much on keeping track of how you evolve with the size, with your choice of, which is your choice of entanglement region. Yes, thank you.
Okay, thank you. Thank you so much, Albert.
Thank you.
Right, so our next speaker is Mauro Napsunciale. He comes from Universidad de Guanajuato, and it's a pleasure for me to introduce him. He's going to talk about a quantum field theory to understand a bit more topics on dark matter. Yes, thank you, Mauro.
Thank you very much, and thank Lorenzo and Luis Felipe for the invitation to give this talk in this meeting. I will review what we have done over the past years with Selim, who is here, and Rodolfo, and some students, and a colleague from Autonomous University in the Coahuila, Simon Rodríguez. I will talk about a very simple and conservative idea, actually, comparing what we have been hearing here. And the original motivation for this was the old problem of the description, quantum field theory for high spin. And then how we approach it and what we find especially for this representation, and from our results and this representation, then we went to dark matter because we found something that we think it is interesting, and then we went to the phenomenology in this part. So we were happy when we found Higgs, and we have the standard model with all the very interesting aspects. Actually, for me, the most impressive construction, intellectual construction of humankind, where we have 3-gauge interactions and do interaction with some freedom, the Higgs self-interaction and the Yukawa couplings with all this variation, which is part of the things that we don't like too much from the standard model. Just want to stress some properties of this. Okay, let me go back to must be this one. Okay, yeah. Just let me stress some things on the standard model, which we don't speak that much. I mean, we are happy because we have the Higgs sector and we can handle things, but there's some things, strange things in this. I mean, from the deep understanding point of view, we start with Poincaré orbit in the Lagrangian, and then we end up with another different orbit, Poincaré orbit, when we do spontaneous symmetry breaking. This transmutation has to do with our classical gravity. It generates also masses from non-gauge Yukawa interactions, and this is, of course, somehow, and we don't know how it is connection. It is connected with gravitation if we consider the equivalence principles. Another thing that I would like to stress is that if we just take, in the spirit of what I'm going to mention in a minute from the standard model, if we take just the standard model as it is with the values of the Higgs mass and the top quark mass, then it will be, we can do calculations. I mean, we don't have this triviality or vacuum instability problems that were discussed for a long time. Of course, it is not the end of the story. We have things that we don't like or do not understand, like we don't know what the origin of the family structure is, these unpleasant mass hierarchies that we have, or the origin of the neutrino masses, the neutrino natures, masses and neutrino natures, and bigger problems, baryon asymmetry, and all this stuff. And now we have not a problem for the standard model, of course, because it was not developed for this, but we know now that all what we have in the standard model is only around 5% of the energy budget of the universe. And we have dark matter and dark energy, and originally I was interested in this. So I will, but this is a quantum field theory meeting, so I will motivate it later once we describe what we have done. If we take a look at the standard model, we can see that we have three key elements here, a base space-time, a gauge group, and a matter spectrum. So what we have been doing for physics beyond the standard model is to modify one of these key ingredients. In the case of space-time, well, we discovered a new symmetry, space-time symmetry, supersymmetry. We also do something in this direction when we do extra dimensional models, and we have all these theories based on these new concepts. In the case of the gauge group, we have the traditional grand unification theories, which enlarge the group and also enlarge the set of particle content of the theory. On the matter content, of course, we have the multi-Higgs model and some other theories, but it has been somehow said here this morning, we don't have still clear signals for this proposal at the LHC yet, in spite of an intensive search in different channels and for different models. So, just to put the elements of my talk, I have to say that in a quantum field theory, if we take this approach, Weinberg approach of quantum mechanical construction, and quantum field theory has a tool to calculate S-matrix elements, then what we have is the particles has with the quantum numbers of the Poincare group, the mass, the spin, and some other which are in these good quantum numbers. And if we want a theory for S-matrix respecting causality, locality, and first principles, then we need fields that transforms into homogeneous Lorentz group representations, and we have this expansion with some coefficients we transform in the Lorentz group. So I will take this point of view, and originally our motivation was to try to construct high-spin field theories, but then we went in a different direction because of what we found. Very simple. The homogeneous Lorentz group is isomorphic to SU2 times SU2. We have two SU2 quantum numbers which classify the representations. If we want parity to be a symmetry, and this it must be for free particles, because they have the symmetries of space-time, then under parity we have these transformations for the generators, and we need to work with not with the AB representations, but with the AB plus VA representations are the minimal spaces. And so the Lorentz groups, the representations are classified like this. And in the standard model, what we have is the Higgs in these representations, quarks and leptons here, and gauge boson in the 1/2. If we go through to supergravity, then we have the gravitino with this representation, and the gravity transforms into 1/1. This is what we have in nature, and the question is, of course, from here we have high spin in the sense that higher than 1. But our question first was if dark matter can be described or has a 1-0-0-1 space-time structure. And then we started, the main question is if this representation, which is the only one with the spin lower or equal to 1, can play a role in the ultraviolet completion of the standard model. And so we started classifying the algebraic structure of in general J0J, and the intention here was to provide a basis for the phenomenological analysis of hadron systems actually. But then, as I said, we found something interesting here and went to dark matter. From the very basic first principles, I mean, we can construct this this A and B, which has to do with rotations and boosts. And we can see that there are some representations where we can define this operator chirality, which is a pseudo-scalar operator. And we will talk actually of 00 1 and J00J in general. Very briefly, in the case of these chiral representations, we can solve from first principles. That means that we can construct those coefficients in the field expansion. And we know explicitly then, I mean, that means that the boosts are connected with the rotation generators. And we know explicitly the Lorentz generator, the parity operator, and chirality operator. So our first goal was to construct a covariant basis. And so the first question was, what is the parity properties, transformation properties? Then we did these very simple calculations, and we can see that in general parity rotates, rotates as a vector, but, rotates as a scalar, but under boost transforms as a vector. So it must have a more complicated structure. So we went to consider this operator, and then we can see that actually this object in general does not behave as a vector under boost. In general, it involves not only the Lie algebra, but the Jordan algebra of the generators, and that means all the set of anti-commutators, and we can construct in general for this all these anti-commutators. Calculating for a particular representation, because this is not, because involves the anti-commutators, it is not general, I mean, it is not a Lie algebra, then we can see that these operators, eventually, we can see that transform has symmetric tensor, whose time component is its parity. We can do the simplest example, the 1/2 0 0 1/2, we know it, and in this case we have this anti-commutator relation, and what we get is a single index, a Four vector operator. It transforms as a Four vector. We can see it. In the case of 1/2 0 0 1/2, what we find is a symmetric traceless tensor, because for three indices, then we go back to the two indices operator. And so the symmetric traceless tensor is this one in terms of the parity and what we know, the generators. The complete algebra, we can calculate it. And in general, for J00J, we can see that P is the complete time component of a symmetric traceless tensor of rank 2J. We were interested in the basis, so a complete basis, not only in this operator, and we followed this very intuitive construction. We know the states because we can construct them from the scratch, and then if we know the states, the operators can be written in terms of the corresponding projectors. These states carry well-defined SU3, homogeneous Lorentz group quantum numbers. Then we can see the problem of identifying this operator is just the problem of the external product and to work out the properties under this group. And it leads us to the Jung tableaux for the group. What we find is a sequence of operators with well-defined symmetries, and has a concrete example. In the case of 1/2 0 0 1/2, we have two scalar operators, 1 0 0 1. These are the homogeneous Lorentz group operators, and two vector operators. The first one are the identity, chirality. This is the S mu that we mentioned before, and chi S mu is the other one that is independent. and the 1001 is homogeneous Lorentz group generators. This is the covariant basis. We have the 16 4x4 matrices. In the case of 1/2, we can do the same exercise. We have two scalars, and one is scalar and the other one is scalar, the identity and chirality. In this case, we have the symmetric mentioned before, traceless operator, and chi S mu nu. The generators and a new operator, tensor operator, matrix tensor operator with the Young-Tabux symmetries, which at the end give us an object transformed like 2, 0 plus 0, 2. The covariant basis in this case is this one. We can do the explicit representation because we know all of them are written in terms of mu nu parity, which is the S00, and chirality. Now, if the question is, what is the constraint or the equation that is satisfied by this field? So we started with the parity projections, and that means I will just put the parity projection eigenvalue equations, then I will boost it, okay, write it in terms of S mu nu, or S mu in this case, this is what happens, or the symmetric in general tensor, and these constraints as seen in an arbitrary reference frames is just this one, where this S is the symmetric traceless tensor. This operator satisfies, we can show these relations, and if we write our classical fields in this form, I mean like plane waves, then we would obtain this equation in configuration space. We can write a Lagrangian for it, and there is the corresponding dagger in this formalism, and we can see that the scalar product here in this space is given by psi dagger psi. We do it for 1/2, and what we obtain is just Dirac equation. The S mu nu in this case there would be gamma mu have this construction, this representation in our constructions, and it coincides with gamma mu matrices in Bayer representation. And if we take a different basis for our space, then we can get different representations of gamma matrices. I mean, different gamma matrices just reflect the basis that we are using in our construction. So from first principles, what we can say is that the director is just a covariant form of rest frame parity projection, and the Dirac algebra is nothing except Jordan algebra for the representation. Then we go for the 1001 representation, and we can work out the algebra of the operators, and started with the same equation, but now for 1/1001. What you obtain is an equation obtained, which was actually obtained by Weinberg in his papers in the 64s, where he studied the possibility of do some Feynman rolls for any spin. This equation is known to have tachyonic solutions. It's an causal theory. It contains two Poincaré orbit, and for the way where it was constructed in that paper, it was not clear what is YO, but we have all the basis for this space, and we can handle this problem. And we see that the problem is that the operator we were using is not a projector when we go off shell, and what we have to do is to use the off shell operator and to project on the correct Poincaré orbit. What you obtain is this equation, okay? And we can show that the solution satisfy, because of the algebra of the S mu nu, satisfy Klein-Gordon, And from here, all is very similar to what we do in textbooks, with some difference which I will mention here. So, summarizing, what we have is a construction of a covariant basis for this space, 6 times 6 matrices. We have 1 plus 1 plus 9 plus 9 plus 6 plus 10, 36 matrices, and the fields satisfies these equations, and it is the same that Dirac equation, in the sense that it goes along the construction based on parity projections. So it is just the eigenvalue equation for parity in an arbitrary frame. Okay, and we have the chirality and we have the basis. Something interesting here is that we have chirality operator, and we can decompose into left and right fields, and what we obtain is that the kinetic term, in this case, couples right and left fields, so we cannot separate, unlike the Dirac case, the left and right component, and so we cannot do chiral gauge theories for this. However, it's possible to have vector gauge interaction. When we saw this, then we thought that maybe it could have something to do with dark matter, but before we made sure that we have a particle interpretation and did the canonical quantization. I will not go through the details, just mention that in this case we have a constraint dynamics. We have to work out the constraints, and we have second-class constraints. It can be solved along the algorithm in the Dirac lectures, all Dirac lectures, and it's very important to say that the sensible quantum field theory we obtain is very important. This algebraic structure. So we do it, and we have 5 minutes to talk about dark matter. Okay. So briefly, the experimental result, main experimental result, because I will leave aside necessarily some of them, but one of them is dark matter relative density. I have no time to discuss this, but we know that we have from experiments this dark matter relative density. We have also information from the galaxy rotation curves. All this is gravity interactions informations. In particular, in our system, we have of the order of 1/3 of a proton per centimeter cubic. We have an intensive search in direct search, I mean dark matter colliding with nuclei, with different kinds of nuclei, and measuring the recoil of the nuclei. And then the most, this is how the collaborations go, and the most competitive right now is Xenon 1T. We will compare our result with Xenon 1T. We have indirect searches where there are some upper bounds on the annihilation of dark matter into different channels, especially mu, photon, tau, E, etc. So we will also compare with these results. And the paradigm for dark matter is the WIMP. It is based essentially in that the necessary sigma b to reproduce the dark matter relative density is of this order, which is of the order of the weak interaction with temperature of the order of 25 times the mass of the particle. However, from all the possibilities that we have in the market, it has been, as we have more and more information, more difficult to comply with the upper bounds. So we have posted the idea that dark matter transforms in the 1001 representations. We construct the effective field theory with a basic principle. The principle is that we have on the one side the standard model particles, on the other side the dark ball, and these particles here have no charge from dark charges, and particles here don't have standard model charge. So we construct on the traditional way the interacting Lagrangian, and for this we need the lowest dimension, which are singlets on one side, and in the standard model we have only dimension 2, which are the lowest one, completely singlets. I mean, this transformed in themselves under any transformation of the standard model. Also this one. And on this dark matter side, we have all these with all these possibilities. I cannot go, because of time, through the details, but this is the most general, the leading interacting Lagrangian. When we do the spontaneous symmetry breaking, we obtain these interactions. The rest is the phenomenology. We have to calculate, for example, if we have dark matter below half the mass of the zeta 0, it will contribute to invisible widths for the zeta 0 and for the Higgs. We have to do the traceology in this formalism to obtain the results. And when we, from the experimental results, we remove the neutrino, antineutrino contribution, we get these constraints for the couplings, and when we compare with the dark matter relative density, sorry, I have no time for this. I have to calculate all the annihilation into all the possible channels in the standard model, and make sure that indeed we have the decoupling of dark matter from the primordial plasma, and here are the results of the constraints of the invisible widths of C and Higgs, and this line is the values consistent with dark matter relative density. The same here, so we are left a very narrow width for the mass of the dark matter. It must be around above 45 GeV. Just will mention that in these experiments we have upper bounds on these channels, and we can calculate in our formalism. It depends on the couplings, and then when we put the couplings and the upper bounds, then we see that they are essentially consistent. More complicated is the direct detection of dark matter, because we have to work out 3 layers essentially of effective theory. I have no time to describe this, just the results. Here we obtain, in the case of the what we call the spin portal, we obtain stronger constraints. I mean, this GT must be small, but in the case of the Higgs portal, we have two possibilities. One of them is completely free, because it gives contribution to the next to leading order, and but one of them, for one of them, we obtain of the order of 10 to the -2. We also calculated now just released the calculations for the photon excess and gamma ray excess from the Milky Way, and we find something which is consistent with this. So the conclusions are there, and up to now, what we have seen, I mean, in our calculation and comparing in this very simple idea with the experimental results, we still have are in the game. I mean, we have this has a possible consistent descriptions of dark matter. Thank you very much.
Thank you, Mauro. We have time for questions.
Is the 1-0 plus 0-1 matter related by SUSY transformation to other representations? And if yes, what would be the possible interpretation of this sector?
Well, first, I didn't mention, but it is for massive fields first. When we study the massless case, which for chirality is important, what we find is a smooth, massive, massless limit. But we know in this case, the 1001, it will be the equivalent, the electric and magnetic fields transform into representations for the massless case. But our construction is actually for massive case. And in that case, it would be the representations we are accustomed to in our work.
Just a very general question. Do you know if it's straightforward to construct a supersymmetric theory with this?
It will be, yeah. Yeah, because it is the same. What is the main advantage of this construction? Is that you do it from the scratch in the sense that all what you are assuming is that you have quantum mechanics. Quantum mechanics with our 6 axioms for our standard quantum mechanics, not entanglement, not this stuff. And the point of view that the quantum field theory is a formalism to calculate the scattering matrix. And that's it. And these representations, the J00J or A00A, has the advantage that you can solve the algebra. That's why but we can do it also, for example, for the 1/2 for the conventional vector representation. You can construct it this way. You can construct the state, you can construct everything. So in principle, there is no obstruction to do it with supersymmetry, which is an interesting work to do.
Okay, so thank you so much, Mar.
Thank you.
So now we have a break and we reconvene at 3:30 in the same room, right? Right, so.